Hello, fellow wanderer of the night. Welcome to this quiet corner of the universe where we explore the cosmos, one gentle breath at a time, where wonder meets rest in the softest possible way. Tonight, we're going to drift together through one of the most beautiful and haunting questions that has ever occurred to human consciousness. Does space ever end? It's a question that might seem simple when you first hear it, perhaps even childlike in its directness. But as we'll discover together over the next few hours, this seemingly innocent inquiry opens doorways into mysteries so profound, so layered with meaning, that they transform how we understand our place in the vastness that surrounds us. Take a moment now to settle yourself completely. Maybe you're preparing for sleep, your body already beginning to release the tensions of the day. Maybe you're in that twilight space between waking and dreaming, where the boundaries of reality become softer, more permeable. Perhaps you're working quietly with headphones, letting these words create a gentle background for your thoughts, or walking through empty streets where the night sky stretches endlessly above you. Before we begin our journey into the infinite, I'd love to ask for your gentle support. If you find peace in these explorations, if these nocturnal wanderings through scientific wonder help you rest or simply satisfy that deep human need to understand our place in the cosmos, please consider giving this video a like. It truly helps this content reach other night-dwelling souls who might need exactly this kind of contemplative exploration into the nature of existence itself. And I'm genuinely curious about you, the person whose consciousness is touching these ideas right now. How do you use content like this? Are you here to fall asleep, letting these cosmic meditations carry you into dreams populated by infinite spaces and curved dimensions? Are you studying, using these gentle explanations to understand concepts that textbooks make feel cold and distant? Are you simply someone who finds comfort in contemplating the vastness that contains us all? From where in this beautiful small world are you listening? Are you in a bustling city where light pollution hides most of the stars we'll be discussing, making you rely on imagination to picture the cosmic dance above? Are you in a rural area where the Milky Way stretches across your sky like a river of ancient light? Are you somewhere in the southern hemisphere, where different constellations tell different stories, or in the far north, where auroras sometimes paint the sky with colours that seem almost cosmic in their otherworldly beauty? Drop a comment and let me know. I read every single one, and your stories of how and why you listen help me understand what these nocturnal explorations mean to people scattered across our small planet, all of us looking up at the same infinite sky, all of us wondering about the same eternal questions. You'll find timestamps in the description for those who prefer to navigate directly to particular cosmic territories, but this is a journey that's designed to be experienced from beginning to end. Each section builds upon the last, creating a gentle spiral of understanding that mirrors the way galaxies themselves spin through the darkness, the way knowledge itself seems to curve back upon itself the deeper we go. Tonight, we're not just asking whether space has an end. We're exploring what it means to exist in a universe that might be infinite, what it feels like to be finite beings contemplating the possibility of endlessness, and how the very question of cosmic boundaries touches something fundamental about human consciousness and our need to understand the container that holds our existence. If your eyes begin to close during our journey, don't worry about missing anything. These ideas will continue to work on your mind even as you rest. The universe itself has been patient for nearly 14 billion years. It can wait while you sleep. And sometimes, the deepest truths about infinity are best understood not through concentration, but through that gentle, drifting state where logic blends with dream, where the boundaries between self and cosmos begin to dissolve in the most peaceful way possible. So breathe with me now. Feel yourself settling into this moment, into this question, into this vast mystery that has no urgency, no deadline, no pressure to solve it quickly. We have all the time in the world, and perhaps all the space too. Closing reflection. And now, as we let our thoughts settle into the quiet vastness of night, we return to the question we began with. Does space ever end? It's no longer the simple question it seemed at the beginning. Like the universe itself, it has expanded, stretched, and deepened through our journey. What began as a search for boundaries has become a meditation on connections, on how every particle, every galaxy, every thought you've had tonight participates in a web that defies edges and dissolves borders. Space, we've discovered, is not a container with walls but a process, a story unfolding, a fabric of relationships. Its mystery is not in where it stops, but in how it keeps creating expansion, transformation, new forms of matter, and even consciousness itself. And in that sense, the question, does space ever end, is not a puzzle to solve, but an invitation to wonder, to recognize that mystery is not something outside of us, but something we are inside of. Because you are not separate from this question. You are part of it. The same expansion that stretches galaxies apart flows in the atoms of your body. The same ancient light that whispers from the cosmic microwave background glows in the warmth of your thoughts. In contemplating space, space contemplates itself, through you. So perhaps space does not end. Perhaps it curves back upon itself, like this narrative returning to its beginning, carrying us in a circle that has no edge, only continuity. Or perhaps it stretches endlessly, without boundaries, without conclusion. Either way, the wonder it inspires is infinite, and wonder, unlike energy, does not dissipate, it multiplies. The more you feel it, the more there is. Thank you, fellow traveller, for joining me on this journey through the silence of the cosmos. If tonight's reflection has brought you peace, or sparked your curiosity, or simply helped you drift into rest, then we have shared something meaningful across the vastness of space and time. So let your eyes grow heavy now, let your breath fall into rhythm with the quiet pulse of the universe. And as you drift into sleep, carry with you the thought that you're not an observer standing outside of space, but space itself, resting, dreaming, becoming aware of its own infinity. And in that awareness there is no ending, only the endless horizon of wonder. Section 1, The Invisible Nature of Space. The void that isn't empty. Picture yourself floating in the deepest darkness you can imagine. No stars, no planets, no glowing nebulae, just you, suspended in what appears to be absolute nothingness. What exactly is that place where you find yourself? What is space when it contains nothing we can see or touch or measure with our familiar instruments? For most of human history, we've thought of space as exactly that. Nothing. A void. An empty stage where cosmic actors perform their ancient dance of gravity and light. But space, as we'll discover together in these quiet hours, is anything but empty. It's one of the most active, mysterious, and profoundly misunderstood aspects of reality itself. The silence of space isn't really silence at all. If you could somehow tune your ears to the right frequencies, you'd hear a constant, gentle hum, not of sound, which can't travel through the vacuum, but of activity, of quantum fluctuations, of the very fabric of reality vibrating with energy so subtle it makes a whisper seem like a shout. Let's begin with something that might surprise you. Even in the most empty-seeming regions of the cosmos, in the vast spaces between galaxies where darkness reigns for billions of miles in every direction, space is buzzing with activity that's invisible to our eyes but fundamental to existence itself. Thanks to quantum mechanics, that beautifully strange branch of physics that describes the behavior of the smallest things, we now understand that empty space isn't truly empty at all. At scales so small, they make atoms look like mountains, far smaller than anything we could ever hope to see directly. Space is alive with what physicists call quantum fields. These fields aren't things sitting in space like furniture in a room. They are space, in a very real sense. Every particle in the universe arises from its corresponding field, like waves forming temporarily on the surface of an infinite ocean. An electron emerges from the electron field, a photon materializes from the electromagnetic field, and even when no particles are present, when space appears completely empty to every instrument we can build, these fields continue their eternal dance. They fluctuate constantly, producing tiny, momentary particles that appear and vanish like cosmic fireflies, too brief to catch but real enough to influence the behavior of everything around them. This restless energy in apparently empty space is called vacuum energy, and it's a bit like the surface of a pond on a still day. From far away, the water looks perfectly calm, smooth as glass, but approach closer and you'll see tiny ripples, gentle disturbances, the occasional jumping of a fish creating concentric circles that spread outward and fade. What seems featureless from a distance reveals itself to be full of hidden motion when examined closely. This is why physicists sometimes say that the vacuum is not empty, it seethes with potential. Virtual particles pop in and out of existence in fleeting pairs, too quick to observe directly but persistent enough to leave their mark on reality. They influence how electrons behave around atomic nuclei. They contribute to the mysterious phenomenon we call dark energy that seems to be pushing the universe apart faster and faster, and they remind us that even nothingness has substance. If your eyes are growing heavy as we contemplate these invisible dancers in the cosmic dark, let them close. There's no need to strain to follow every detail. Sometimes the most profound truths about the universe are better absorbed than analysed, better felt than thought. Your mind will continue processing these ideas even as you drift toward rest. So no, space is not just the place where you lose your keys or where your thoughts wander during long meetings. It's alive with structure and movement and possibility, even when there's nothing visible to any eye that has ever evolved on any planet circling any star. And this is just the beginning of space's mysteries. Consider this: space itself can expand, not the things in it moving farther apart like dots on a balloon that's being inflated, but space itself stretching between objects, creating more room where there was less room before. That idea comes from Einstein's theories and forms the foundation of our modern understanding of cosmology. But let's pause here. In this moment of wonder mixed with confusion, it's easy to feel overwhelmed by the idea that the emptiest thing in existence is actually humming with energy and geometry and fields we can never directly perceive. Yet in a way, this makes the universe more comforting, not less. It means that even in the cosmos's quietest, loneliest moments, there's still something happening. A soft background presence like the quiet crackling of a fireplace, or the gentle rustle of leaves on a windless night. And that presence, those fluctuations, that restless vacuum energy, reminds us that space isn't simply the absence of matter. It's a physical entity with properties of its own. It can bend and stretch and expand and ripple. It has energy. It has temperature. Even the vast emptiness between galaxies is thought to be a few degrees above absolute zero, still faintly warmed by the leftover glow of the Big Bang itself. When we ask, what is space? We're not talking about an empty container. We're talking about a rich, structured fabric that connects every atom, every galaxy, every living being that has ever wondered about the stars. Space is not where things happen. Space is one of the things that happens. It's part of the story, not just the stage where the story unfolds. And perhaps that's the most beautiful thing of all. The more we study space, the more it refuses to be empty. It twists and hums and fluctuates and expands. Even when it seems to do nothing, it's never really doing nothing at all. Like consciousness itself, space appears to be one of those fundamental aspects of reality that exists not as a thing, but as a process, not as a container, but as a connection. As we'll discover together in the hours ahead, this active living space sets the stage for questions even more profound than what space contains. It opens the doorway to wondering whether space itself ever comes to an end, and what such an ending might even mean in a universe where nothingness itself is full of something. Section 2, the observable universe. Our cosmic bubble of light. Imagine standing in a meadow on a foggy morning, the world around you soft and grey and mysterious. You can see perhaps 50 meters in any direction before the fog swallows everything in gentle obscurity. You know the world continues beyond that misty boundary. There are hills and trees and streams and other meadows stretching far beyond your vision. But for now, your world is contained within that circle of clarity, that bubble of the visible. This is remarkably similar to our situation when we gaze out into the cosmos. No matter how powerful our telescopes become, no matter how sensitive our instruments, there's a fundamental limit to how far we can see into the universe. Not because space ends there, not because we lack sufficiently advanced technology, but because of something far more profound. The universe itself has a history, and light takes time to travel. This boundary of the visible cosmos is what astronomers call the observable universe, and it forms a kind of cosmic bubble around us, not a barrier in space, but a horizon in time. It's the furthest distance from which light has had the opportunity to reach us since the universe began its expansion nearly 14 billion years ago. Now, you might think logically that if the universe is about 13.8 billion years old, then the farthest we could possibly see would be about 13.8 billion light years away. After all, that's how long light has had to travel toward us since the beginning of everything. If light moves at, well, the speed of light, wouldn't that define the edge of our vision? Ah, if only the universe were that straightforward, that predictable in its geometry. But because of the way space itself expands, remember that active, living space we discussed? That boundary is actually much farther away than simple arithmetic would suggest. The observable universe has a current radius of about 46.5 billion light-years in every direction, making it roughly 93 billion light-years across. Yes, you heard that correctly. Even though the universe is only 13.8 billion years old, the distance to the farthest galaxies we can observe is more than 3 times that age in light-years. This happens because space has been stretching the entire time light has been travelling toward us. Think of it like this, and let your mind relax into the analogy. Imagine you're watching someone bake bread, and they've placed raisins throughout the dough before putting it in the oven. As the bread rises, the raisins move farther apart from each other. Now imagine that at the moment the bread begins to rise, one raisin emits a tiny flash of light toward another raisin. By the time that light arrives at its destination, the bread has expanded significantly. The photon's journey wasn't across a static distance, it was across a growing one. The destination raisin drifted farther away, even as the light was travelling toward it. That's essentially what happens on the cosmic scale. The light from distant galaxies has been travelling toward us for billions of years, but space itself has been expanding during that entire journey, stretching the distance that light had to cross. By the time ancient photons reach our telescopes, the galaxies that emitted them are much farther away than they were when the light began its journey. This brings us to one of the most beautiful concepts in cosmology, the cosmic horizon. It's not a wall that you might fly a spaceship toward and suddenly encounter like running into the edge of a map. Instead, it's more like a gentle fading of information, a soft boundary where our knowledge dissolves into mystery. Beyond this horizon, light from distant regions simply hasn't had enough time to reach us since the Big Bang began the universe's expansion. It's as if we're standing in a vast fog of time and distance, able to see only the nearby glow while the rest remains shrouded. Not because it's not there, but because the universe hasn't yet delivered us the signal that would reveal it. If you feel your consciousness beginning to drift as we contemplate these vast scales, let it. There's something profoundly restful about imagining yourself at the centre of a cosmic bubble, surrounded by billions of years of light slowly arriving from the depths of space and time. You don't need to hold on to every detail. Sometimes the most important understanding comes not from grasping facts, but from letting yourself be held by wonder. This horizon that surrounds us is constantly changing, constantly evolving. As time passes, light from more distant regions has the opportunity to complete its journey to our small corner of the cosmos, and our bubble of the observable expands. We see deeper into space, which means we see further back in time, watching the universe's history unfold in reverse as we peer into increasingly ancient light. But here's where the story takes a melancholy turn that's somehow also beautiful. Because of something called dark energy, a mysterious force that appears to be accelerating the expansion of space itself, some galaxies are moving away from us so quickly that the light they're emitting now will never reach us. Not in 1 trillion years, not in 1 quintillion years, not even if we wait until every star in the universe burns out and space grows cold and dark. These distant galaxies are receding faster than light itself can travel, not because they're breaking any cosmic speed limit, but because the space between us is stretching too rapidly for light to make progress across the growing gap. In a very real sense, the universe is slipping away from us, one galaxy at a time, like pages being torn from a book we're still trying to read. To put it another way, imagine trying to walk towards someone on a treadmill that's moving backward. If the treadmill moves faster than you can walk, you'll never reach your destination, no matter how persistent you are. That's what's happening to light from the most distant galaxies. It's trying to cross space toward us, but space is expanding away faster than light can close the gap. There's something quietly profound about this realization. It means that everyone, everywhere in the universe, has their own observable universe, their own cosmic bubble of the visible. If you were somehow transported to a galaxy 10 billion light years away, your bubble would overlap with ours in some regions, but it would also include vast territories that will forever remain invisible to us. The observable universe isn't the universe. It's just our particular slice of it, our personal window into infinity. And what a slice it is. Within our cosmic bubble, astronomers estimate there are roughly 2 trillion galaxies, each containing billions or trillions of stars. That's an almost incomprehensible amount of starlight filling our little observational domain. The photons from some of these galaxies have been travelling toward us for so long that they began their journey before Earth had even formed, before our solar system condensed from cosmic dust, before the first organic molecules found each other in the primordial seas of countless worlds. As you rest in the knowledge of this vastness, remember that some of the light touching your eyes tonight, whether from stars visible through your window or from the screen where you're reading these words, began its journey before complex life existed anywhere in the observable universe. You're literally seeing ancient history, cosmic messages in bottles that have been floating through space and time for eons just to reach this moment of your awareness. And yet, as rich and magnificent as our observable universe is, it may represent only the tiniest fraction of what's actually out there. Beyond our cosmic horizon, space might continue forever, filled with structures and stories and perhaps even other forms of consciousness, wondering as we are whether the vastness ever finds an end. There's a peculiar peace in knowing that we can't see everything, in accepting that our place in the cosmos is fundamentally local. We don't need to understand or observe the entire universe to find meaning in our small corner of it. Sometimes it's enough to sit beneath whatever stars are visible from your particular patch of Earth and know that you're part of something immeasurably larger than yourself. The observable universe is like a slowly expanding gift, allowing us to see deeper into the cosmic story with every passing day. It's not a prison that confines our knowledge, it's a window that gradually opens wider, revealing more of the infinite mystery that contains us all. Section 3, Looking Back in Time. When every star is a time machine, close your eyes for a moment and imagine this. Every time you look up at the night sky, you're not seeing the universe as it is right now in this instant. You're seeing the universe as it was, sometimes minutes ago, sometimes millions of years ago, sometimes billions of years into the past. Every star, every galaxy, every faint smudge of light in the darkness is a time capsule, carrying information from earlier chapters of cosmic history. Looking across the universe is remarkably like rummaging through a vast attic, filled with photographs from different eras, each image capturing a moment from the cosmic past. The farther away something is, the older the image we're seeing, the deeper into history we're peering with each photon that reaches our eyes. Let's start with something close to home to ease into this concept. When you look at the sun, please don't actually look directly at it, but imagine its warm light on your face. You're seeing it as it was about 8 minutes ago. That's how long it takes light to travel the 93 million miles from the sun's surface to Earth. The sun could, hypothetically, vanish right now, and you wouldn't know for 8 minutes. You'd continue feeling its warmth, seeing its light, living in a present moment that was actually 8 minutes in the past. Stretch that concept to the nearest star visible to the naked eye. Proxima Centauri, our closest stellar neighbour, is about 4.2 light-years away. When you see its faint light, you're seeing it as it was when you were about 4 years younger than you are right now. If something dramatic happened to that star today, if it suddenly flared or dimmed or changed colour, you wouldn't know about it until 4 years from now. Now let your mind expand gently to consider more distant stars. Sirius, the brightest star in our night sky, is about 8.6 light-years away. The light reaching your eyes left that brilliant star when you were nearly a decade younger. Betelgeuse, that red giant in the constellation Orion that might explode in a spectacular supernova someday, is roughly 650 light-years distant. The red light you see from Betelgeuse tonight began its journey toward Earth, around the time when human beings were first building cathedrals and wondering about their place in the cosmos. If you feel yourself drifting as we travel deeper into these cosmic distances, let yourself drift. There's something deeply soothing about imagining light as a patient traveller, carrying messages across the darkness for hundreds or thousands of years just to arrive at the moment of your awareness. But let's continue our journey backward through time. The Andromeda Galaxy, our nearest major galactic neighbour, is about 2.5 million light-years away. When you spot its faint smudge in the night sky, if you're fortunate enough to be somewhere dark enough to see it, You're looking at light that began its journey toward Earth before our species existed, before our ancestors walked upright, before the ice ages that shaped the continents we call home. Some of the galaxies visible through powerful telescopes are so distant that their light has been travelling toward us for over 13 billion years. These ancient photons began their journey when the universe was young and small and hot, when the first stars were just beginning to forge heavy elements in their nuclear furnaces, when galaxies were still learning how to spin and organise themselves into the cosmic web we observe today. This leads us to something astronomers call look-back time, a way of expressing how far into the past we're seeing when we observe distant objects. If a galaxy is 8 billion light-years away, its look-back time is 8 billion years. That light has been travelling across space for more than half the age of the universe, crossing unimaginable distances, surviving the expansion of space itself, arriving just in time to illuminate your evening contemplation of infinity. In a strange and beautiful way, space is full of ghosts, echoes of what once was, preserved in the amber of ancient light. We're not seeing the universe as it exists in this moment. We're seeing it frozen in earlier chapters of its existence, like a vast museum where every exhibit is from a different era, and the deeper you walk into the galleries, the further back in time you travel. Some of the galaxies we observe may not even exist anymore in any form we would recognise. They might have collided with other galaxies, transforming into entirely new cosmic structures. They might have exhausted their star-forming gas and faded into quiet darkness. They might have been torn apart by the expansion of space itself, their stars scattered like seeds on cosmic winds. What we see is a kind of fossil record written in photons, a cosmic archaeology where every point of light is an artifact from the past. But it becomes even more fascinating when you consider how this light has been transformed during its long journey. As photons travel through the expanding universe, the space they're moving through stretches, and the light itself gets stretched along with it. This phenomenon is called redshift, and it's similar to how the pitch of an ambulance siren drops as it moves away from you. Just as sound waves get stretched when their source is receding, light waves get stretched when the space they're travelling through is expanding. Since space itself has been growing throughout cosmic history, nearly all distant galaxies are being carried away from us by this expansion, and their light becomes stretched into longer, redder wavelengths as it travels. By measuring the amount of redshift in light from distant galaxies, astronomers can determine not just how far away they are, but how long that light has been travelling through expanding space. High redshift means a very distant galaxy, and a very ancient glimpse into the early universe, when galaxies were younger, smaller, and often more chaotic than the mature spiral and elliptical galaxies we see in our cosmic neighbourhood. This redshifted light holds encoded stories about the structure, age, and history of the cosmos. It tells us how fast the universe is expanding, how galaxies evolve over cosmic time, and it even provides clues about mysterious forces like dark energy that appear to be shaping everything on the grander scales. Every colour-shifted photon that reaches our instruments is a messenger from the past, carrying information about conditions that existed billions of years ago. If you're finding comfort in this idea of light as cosmic mail, of photons as patient messengers carrying news from the deep past, let that comfort settle into your bones. There's something profoundly peaceful about the realization that the universe is constantly sending us messages, that every moment we spend looking up is a moment of receiving ancient communications from across the vastness of space and time. Our telescopes, from backyard instruments to the most sophisticated space observatories, are essentially time machines. When you look through a telescope, you're not just seeing things more clearly, you're seeing them more deeply into the past. A small telescope might show you Jupiter's clouds from about 40 minutes ago, when that light left the giant planet and began its journey across the solar system to your eye. A more powerful observatory might reveal a galaxy as it appeared 500 million years ago, back when life on Earth was still experimenting with hard shells and complex eyes, when the first vertebrates were learning to walk on land. The great space telescopes like Hubble, James Webb, and their successors can peer so far into space, and thus so far back in time, that they capture the faint light of some of the first galaxies to ever form, structures that began taking shape just a few 100 million years after the Big Bang itself. There's something beautifully ironic about this relationship between distance and time. In our quest to understand the future of the universe, we spend most of our time staring into its past. But that's the nature of light in an expanding cosmos. It travels fast, incredibly fast, but not instantly. And because the universe is so vast, even light has to work hard to keep up with the expansion of the very space it's travelling through. This means that the universe as we experience it is always slightly out of date, like watching a movie that's still being edited, with scenes arriving one at a time, often out of chronological order. Some light arrives from nearby galaxies that are relatively young and recent, while other photons bring us news from the universe's infancy, when conditions were so different that they barely seem like the same cosmos we inhabit today. Yet this delay, this cosmic lag between event and observation, is also a tremendous gift. Without it, we would never be able to piece together the story of how everything came to be. The gradual arrival of ancient light lets us see different stages of the universe's evolution all at once, like pages from a novel scattered across the sky, each one offering glimpses into different chapters of the cosmic story. The result is a kind of temporal patchwork spread across the night sky. In one direction, you might see a relatively nearby galaxy that formed recently, still young and active in its star formation. In another direction, your telescope might capture the flickering light from billions of years ago, when the universe was denser, hotter, and stranger than anything in our current cosmic neighbourhood. All of these images are layered not just across space, but across time itself. You could say we're living inside a museum made entirely of light, where instead of walking from exhibit to exhibit, we let the photons come to us, crossing unimaginable distances to tell their stories, to fill our sky with ancient news from the dawn of everything. There's something quietly magical about realizing that every time you look up at the stars, you're gazing into a time machine powered by nothing more complex than the patient travel of light across the darkness. The light brushing against your retina may have started its journey before the first tree grew on Earth, before the first cell divided, before the first atmosphere learned to hold its breath. And all of this knowledge, all these insights into the deep history of the cosmos, comes from simply listening to the light. By studying its colours, its intensity, its redshift, we unlock a silent language that has been spoken across billions of years. It's a language that doesn't just describe the universe. In a very real sense, it is the universe, encoded in motion and memory and the gentle patience of photons crossing the void. If your thoughts are becoming as soft and distant as the light we're discussing, embrace that feeling. The universe has been patient for nearly 14 billion years. It can wait while you rest. Sometimes the deepest truths about time and space are best absorbed in that gentle state between sleeping and waking, where the boundaries between self and cosmos become as soft as starlight. Next time you see a star twinkling in the darkness above your home, remember that you're not looking at it as it is in this moment. You're looking at a version of it preserved in time, a glimmer of history still racing through the darkness toward your awareness. You're seeing what the universe looked like when it was younger, and perhaps in some ways more innocent, less stretched by the long march of cosmic time. And through the patient work of science, with the gentle help of light itself, we continue to piece together our origin story, one distant glow at a time, one ancient photon at a time, building an understanding of where we came from by watching where we've been. Section 4. The Cosmic Horizons. Boundaries. Made of time. Itself. Picture yourself standing on a beach at dawn, watching the horizon where the ocean meets the sky. It's a gentle, curved line that seems to mark the edge of the world, though you know the ocean continues far beyond what your eyes can reach. The horizon exists not because the ocean ends there, but because of the curvature of the Earth and the limitations of your perspective. Cosmic horizons work in remarkably similar ways, except instead of being limited by the curve of a planet, we're limited by the curve of time itself, by the finite age of the universe and the speed at which information can travel through space. These horizons define the boundaries of our cosmic knowledge, not because space ends at those boundaries, but because time hasn't yet allowed us to see beyond them. Unlike the tidy horizon where sky meets sea, cosmic horizons come in several different varieties, each with its own rules and significance, each telling us something different about the nature of space and time and the limits of what we can know about the universe we inhabit. The first and most fundamental is called the particle horizon, and it marks the maximum distance from which light or any other signal could have reached us since the universe began its expansion. Think of it as the ultimate boundary of our current cosmic bubble, the outermost edge of everything we can currently detect or observe. This particle horizon is shaped by time itself. Since the universe has existed for approximately 13.8 billion years, and since space has been expanding during that entire period, the farthest distance that light could have travelled to reach us today is roughly 46.5 billion light-years in any direction. That's why the observable universe is approximately 93 billion light-years across. It's the grand perimeter of everything we have access to, the circumference of our cosmic awareness. But don't mistake this horizon for a wall or barrier. There's no glowing edge with warning signs, no cosmic customs office checking passports. Instead, it's a limit woven into the very fabric of time and causality. Like standing on the shore of an infinite ocean, you can look out as far as the light allows, but you'll never see beyond that gentle curve where time itself creates the boundary. If you feel your mind beginning to drift as we contemplate these vast boundaries, let it drift. Sometimes the most profound truths about infinity are best understood not through concentration, but through that soft, receptive state where thoughts flow like tides, where understanding comes not from grasping but from allowing. Next comes what's called the event horizon of the universe, not to be confused with the dramatic version that surrounds black holes. In cosmology, the event horizon refers to a boundary beyond which events can never affect us, no matter how long we wait. It's a cosmic line in the sand drawn not by space but by the expansion of space itself. Anything beyond this event horizon is retreating from us faster than the speed of light, due to the accelerating expansion driven by dark energy. Light emitted from beyond this boundary will never catch up to us, no matter how patient or persistent it might be. It's like trying to send a message to a friend on a boat that's drifting away down a river, where the current flows faster than any messenger could swim. At this very moment, the cosmic event horizon is estimated to be around 16 billion light-years away. This means there are regions of the universe we can see now, galaxies whose ancient light is still reaching us. But if those same galaxies emit new light today, that light will never complete its journey to Earth. We're watching cosmic structures that are, in a very real sense, slipping away from us forever. This creates a poignant situation. We can observe galaxies that are simultaneously visible and unreachable. We can see their past, but we'll never see their future. It's like watching the taillights of a car that has just turned a corner. You can still see the glow, but the car itself is already gone, travelling down a road you'll never follow. Finally, there's what's sometimes called the cosmological horizon, a more general term that encompasses these observational limits and reminds us that horizons in space are deeply tied to the physics of the universe itself. This horizon represents the moving edge of our cosmic awareness, the boundary between the known and unknowable that expands outward as time passes and more light has the opportunity to reach us. These horizons are constantly shifting and evolving, like tides that operate on cosmic timescales. As the universe ages, the particle horizon grows larger. More light has time to reach us from previously invisible regions. But because of dark energy and the accelerating expansion of space, the event horizon becomes more restrictive. More galaxies slip beyond the reach of future communication. The universe becomes a place of increasing isolation, not because it's becoming empty, but because the light from its distant corners is falling farther and farther behind the expansion of the space it's trying to cross. It's like trying to mail a letter across a river where the opposite shore is drifting away faster than any postal service could manage. To understand this better, imagine the universe as a slowly inflating balloon with dots scattered across its surface. As the balloon expands, the dots move farther apart from each other. We can only see the dots that are close enough for their light to make the journey to us. Beyond a certain distance, the balloon is expanding so rapidly that light from those distant dots can never catch up. There's something haunting, but also peaceful about these cosmic limits. They serve as a gentle reminder that we're not omniscient observers of reality. Our view of the universe is shaped by cosmic history, by the finite speed of light, and by the strange properties of the expanding space that light travels through. We're peeking through a window that's enormous, yes, but still finite in its scope. Some regions of the universe will always remain mysteries, no matter how patient we become, no matter how clever our instruments grow. Not because we lack the technology to see them, but because of the fundamental nature of space-time itself. These unseen realms aren't hidden behind a curtain waiting to be pulled back. They exist beyond the reach of information, forever unknowable. And yet, even within these boundaries, we've managed to learn extraordinary things about the cosmos. We've mapped the distribution of galaxies, measured the afterglow of creation itself, and traced the fingerprints of the Big Bang and the cosmic microwave background radiation that still bathes the universe in its gentle glow. The horizons don't limit our imagination. They frame it like the borders of a painting that somehow make the artwork more beautiful rather than constraining it. Like the morning sun burning off fog to reveal more of the landscape, every new discovery pushes our cosmic horizons back just a little, revealing more of the vast territory that surrounds our small island of awareness. But some regions will always remain hidden behind the curve of space-time, behind the stretching, swelling boundary where light will never arrive, and perhaps that's as it should be. Perhaps part of the beauty of existence lies in knowing that there are mysteries we'll never solve, territories we'll never map, stories we'll never read to their conclusion. Still, here we are, spinning quietly through space on our small planet, watching photons arrive from billions of years ago, reading the messages they carry about the deep history of everything, and dreaming about what lies beyond the next soft bend in the cosmic road. Even if we can't see it all, even if vast regions of reality remain forever beyond our reach, there's profound beauty in the attempt. In listening to the quiet whispers of ancient light, in following photons to the very edges of the knowable, and in recognizing that while we may never see the complete picture, we're privileged to be part of the story being told across the vastness of space and time. If your consciousness is beginning to settle into the rhythm of cosmic patience, if the vast scales of time and distance we've been discussing are creating a gentle heaviness in your thoughts, let that settling continue. The universe has been patient for nearly 14 billion years. It can wait while you rest. Sometimes the deepest truths about cosmic horizons are best absorbed during the gentle transition between waking contemplation and the peaceful embrace of sleep. The horizons don't limit our imagination. They frame it, like the borders of a painting that somehow make the Section 5 the expanding fabric. When space itself stretches, not too long ago, in the relatively brief span of human scientific inquiry, most people believed the universe was essentially static. Galaxies existed out there in the darkness, stars shone with their ancient light, and everything more or less stayed put. It was a picture of cosmic stability, of a quiet, eternal cosmos that had always been roughly as it is and always would be. But in the early 20th century, a discovery emerged from mountaintop observatories that would forever change our understanding of space itself. The universe, it turned out, wasn't sitting still at all. It was growing, stretching, expanding in ways that challenged every assumption about the nature of cosmic space. It was Edwin Hubble, yes, the same name we gave the famous space telescope that has spent decades peering into the cosmic deep, who first noticed something peculiar about the light from distant galaxies. While studying their spectra, the cosmic fingerprints that reveal their composition and motion, he observed that their light was consistently redshifted. This meant the galaxies were moving away from us, and more importantly, the farther away they were, the faster they seemed to be receding. This wasn't a random pattern or a cosmic coincidence. It was a universal law, a fundamental property of the cosmos itself. Space, it appeared, was expanding. Let your mind rest gently on this concept for a moment. The very fabric of reality, the stage upon which every cosmic drama unfolds, is not fixed or static. It's growing, stretching, creating more room where there was less room before. If you find this idea dizzying, let yourself be dizzy. Some truths about the universe are meant to be felt rather than fully comprehended. Now, this expansion isn't quite like galaxies zooming through a fixed, static space, like cosmic race cars speeding through an eternal racetrack. It's not as if they're bursting outward into a pre-existing void, leaving empty space behind them. What's actually happening is far stranger and more elegant than simple motion through space. Space itself is growing, expanding, creating new distance where none existed before. Imagine that space is like bread dough, and galaxies are raisins embedded throughout that dough. As the dough rises in a warm oven, it stretches in every direction simultaneously. Each raisin finds itself farther from all the others, not because any individual raisin is moving through the dough, but because the dough itself is expanding, creating more space between them. This is how the universe works on the larger scales. Galaxies aren't rushing outward through space like projectiles from some cosmic explosion. They're being carried away from each other as the fabric of space itself stretches, creating new cosmic real estate in the vast spaces between galactic neighborhoods. That's why, no matter where you might be in the universe, it would appear that everything else is moving away from you. From every galaxy's perspective, space is expanding in all directions. It's like being inside a rising souffle. No matter which bubble you find yourself in, all the other bubbles seem to be drifting away, carried by the expansion of the delicate structure that contains them all. The universe isn't expanding into anything in particular. There's no outer boundary it's approaching, no larger container it's filling. The expansion is intrinsic to space itself. Distances between unbound objects simply grow over time, as if the cosmic measuring tape was slowly but steadily lengthening. This idea of universal expansion was so radical, when Hubble proposed it, that even Albert Einstein had to reconsider his own equations. Originally, Einstein had added something called the cosmological constant to his general theory of relativity, specifically to keep the universe static. He thought the cosmos had to be unchanging, eternal in its configuration, but his mathematical equations left to their own devices suggested otherwise. When Einstein learned about Hubble's observations of galactic recession, he famously called his addition of the cosmological constant his greatest blunder. Though in one of those beautiful ironies that science sometimes provides, the concept has since made a comeback in our attempts to understand dark energy and the accelerating expansion we observe today. The universe, it seems, has a sense of humour about human assumptions. If your breathing is beginning to slow as we contemplate these vast motions of space and time, let it slow. There's something deeply restful about imagining the universe as a gentle expansion, unhurried and inevitable, like the slow rising of bread in a warm kitchen or the gradual unfurling of a flower in time-lapse photography. But let's return to the expansion itself and what it tells us about the nature of space. One of the most beautiful consequences of Hubble's discovery is that it allowed scientists to essentially rewind the cosmic clock. If galaxies are all moving away from each other now, they must have been closer together in the past, much closer. This backward extrapolation led to the idea of a hot, dense beginning to the universe, what we now call the Big Bang, though that term can be misleading, suggesting some kind of explosion in space like fireworks going off in a dark field. The Big Bang was more like the rapid swelling of space itself, everywhere at once, with no centre and no blast radius, just the entire universe stretching out from a state of extreme density and heat. You can't point to a location in the sky and say that's where the Big Bang happened, because it happened everywhere, including right where you're sitting as you listen to these words. The expansion began at every point in space simultaneously, and it's still continuing today, nearly 14 billion years later. This expansion doesn't affect everything equally, which is important to understand as you let these ideas settle into your consciousness. The stretching of space works on the grandest scales, between galaxies and galaxy clusters, but it doesn't pull your morning coffee farther from your lips or separate the atoms in the chair you're sitting in. Gravity and other fundamental forces dominate on smaller scales, keeping local structures nicely bound together. The Milky Way isn't expanding, your neighbourhood definitely isn't expanding, and unless your washing machine has developed mysterious cosmic properties, even your sock drawer remains relatively stable in its spatial dimensions. But on the cosmic level, in the vast spaces between galactic superclusters, the expansion continues its patient work. And what's more remarkable still, this expansion is accelerating. This discovery, made in the late 1990s by teams of astronomers studying distant supernovae, came as a complete surprise. Scientists had assumed that gravity would gradually slow down the cosmic expansion, like friction eventually bringing a spinning wheel to rest. Instead, they found evidence of a mysterious force, now called dark energy, that appears to be causing the expansion to speed up over time. The cosmic dough isn't just rising, it's rising faster and faster with each passing moment, driven by something we don't yet understand but can observe in the behaviour of distant galaxies. No one knows exactly what dark energy is. It might be an inherent property of space itself, energy that emerges from the quantum vacuum we discussed earlier. It might be a field we haven't yet learned to detect directly. Or it might be something even stranger, a fundamental aspect of reality that we're only beginning to glimpse through its effects on cosmic expansion. Whatever dark energy is, It now dominates the energy budget of the universe. That gentle stretch we observe is turning into something more like a cosmic sprint, with galaxies receding from one another at ever-increasing speeds, carried by the accelerating expansion of the space between them. There's something quietly poetic about this accelerating expansion. The universe began with everything close together, dense and unified in ways we can barely imagine. Over billions of years, it expanded and cooled, forming the first stars and planets, and all the ingredients that would eventually become life. And now it continues to stretch outward, stars aging, galaxies moving apart, space growing like a story that opened with tremendous energy and is now drifting into an infinite gentle epilogue. If there were sound in space, which there isn't, but if there were, perhaps it would be like the soft creaking of rising dough, the occasional pop of a bubble forming and dissolving, the slow whisper of infinite expansion. Not a violent noise, not an urgent sound, just the peaceful hum of a universe gradually becoming itself. If you're feeling drowsy as we contemplate this cosmic stretching, embrace that drowsiness. The expansion of the universe is the most patient process imaginable. It's been continuing for nearly 14 billion years and shows no signs of hurrying. You can rest in the knowledge that this vast, slow dance of space and time will continue whether you're awake to observe it or not. When astronomers say the universe is expanding, they're not talking about objects flying away from some central point like debris from an explosion. They're describing the most fundamental property of space itself, its capacity to grow, to stretch, to create new room in the cosmic house where before there was less room. It's one of the most profound discoveries in the history of science, and also one of the most comforting. The idea that change can be gradual, patient, and ultimately beautiful. That the universe doesn't rush toward its destiny but unfolds with the kind of gentle persistence we might associate with seasons changing, or tides flowing, or the imperceptible growth of trees reaching toward the sky. And as we sit here on our small planet, surrounded by stars whose light carries messages from the deep past, we're part of that expansion. Every breath you take, every heartbeat, every moment of consciousness occurs within space that is quietly, patiently, beautifully growing larger with each passing second. It's enough to make you feel simultaneously infinitesimal and cosmically significant, a temporary arrangement of atoms experiencing the universe's own gentle breathing, its slow and steady expansion toward whatever infinite future awaits in the darkness ahead. Section 6. Faster than light. When space breaks its own speed limit. In the world of physics, there's a rule that seems absolutely fundamental, carved into the very bedrock of reality itself. Nothing can move faster than light. Not a spaceship, not a signal, not even your quickest thought racing from neuron to neuron in your brain. According to Einstein's theory of relativity, the speed of light, approximately 300 million meters per second, is the universal speed limit, the cosmic constant that governs the maximum rate at which information can travel through space. And yet, as you rest in the gentle darkness of your evening, astronomers have observed something that appears to challenge this sacred rule. There are galaxies out there in the deep cosmos that seem to be moving away from us faster than light itself. Entire clusters of stars and cosmic dust slipping beyond our reach at what physicists call superluminal speeds. It sounds like the universe should be issuing cosmic speeding tickets, like physics itself should be in a state of emergency. But don't worry. Let your mind settle easily with this apparent contradiction. Everything is fine. The universe isn't breaking its own rules. It's simply playing a very elegant game with them, demonstrating once again that reality is far more subtle and beautiful than our everyday intuitions might suggest. To understand what's really happening, we need to revisit that key idea we touched on earlier. Galaxies aren't actually flying through space like cosmic projectiles launched from some universal cannon. Instead, space itself is expanding, and galaxies are being carried along with it like leaves floating on the surface of a slowly rising flood. Think of space as an enormous rubber sheet with dots painted across its surface. If you stretch the sheet gently but persistently, the dots move farther apart from each other, not because they're crawling across the surface under their own power, but because the surface itself is growing beneath them. This is how galaxies can appear to recede from each other faster than light. It's not that they're violating the speed limit, but that the space between them is stretching so rapidly that the total separation increases at a rate greater than light can bridge. The galaxies themselves remain perfectly obedient citizens of physics, never exceeding the speed of light in their local reference frames. It's space that's doing the heavy lifting, the cosmic stretching that carries them along. Here's a gentle analogy that might help as your thoughts begin to soften towards sleep. Imagine you're standing on a treadmill that's gradually speeding up. You try to walk towards someone at the other end, but the treadmill is moving backward faster than you can walk forward. Eventually, no matter how much effort you expend, the distance between you and the other person keeps increasing. It's not that you're walking too slowly, you might be walking at your maximum speed. It's that the ground beneath you is working against your motion. In the case of our expanding universe, light is trying to travel through space toward us. But in the most distant regions, space is expanding so rapidly that photons never make progress in our direction. They're like swimmers trying to move upstream during a flood. No matter how fast they swim, the current carries them farther away from their destination. This doesn't violate relativity because Einstein's theory only prohibits objects from moving through space faster than light. It says nothing about how fast space itself is allowed to grow or stretch, and it turns out that space has quite a flair for dramatic expansion when the conditions are right. Consider, for example, a period called cosmic inflation, a mind-bendingly brief moment just after the Big Bang when the universe expanded at absolutely staggering rates, far exceeding the speed of light. In less than a trillionth of a second, the entire observable universe grew from something smaller than a proton to something larger than a grapefruit, and possibly much larger still. If you were to try to explain that rate of expansion in everyday terms, you might say it's like a grain of sand suddenly becoming larger than the solar system in the time it takes light to travel the width of that same grain. It's a transformation so rapid and so dramatic that it challenges our ability to find adequate analogies in the world of human experience. And again, this faster-than-light expansion didn't break any cosmic laws. It was space performing the expansion, not particles racing through it. It's one of the rare instances in physics where faster-than-light travel is not only allowed, but essential for explaining the universe we observe today. This period of cosmic inflation had profound consequences that we can still observe billions of years later. It smoothed out the early universe, ironing away irregularities and unevenness like a cosmic steam press, working on the fabric of space-time itself. It also helps explain why the universe looks so remarkably uniform in every direction, despite the fact that distant regions haven't had time to exchange information or influence each other through any known physical process. If your mind is beginning to feel as stretched as the space we're discussing, let it stretch. Sometimes the most important insights come not from forcing understanding, but from allowing yourself to be gently overwhelmed by the sheer scale and strangeness of cosmic reality. Even now, billions of years after that initial period of inflation, space continues to expand, carrying distant galaxies farther and farther away from us. Some of those galaxies are now receding faster than light, not because they've somehow accelerated beyond the speed limit, but because the space between us is growing faster than light can close the gap. This means there are regions of the universe we can never hope to see, no matter how long we wait or how patient we become. Their light will never reach us because the space it must cross is expanding too rapidly. If those distant galaxies emit new light today, that light will be swept away into the deepening void, carried backward by the tide of cosmic expansion. These galaxies aren't lost because they're moving too fast through space. They're lost because the road between us is lengthening faster than their signals can travel. It's like trying to send a message across a river where the opposite shore is drifting away faster than any boat could row, faster than any bird could fly. Eventually, in this scenario, even the concept of communication becomes meaningless. The distance grows so vast, the expansion so relentless, that the very idea of connection across such gaps transcends physical possibility. So when astronomers speak of galaxies receding faster than light, they're describing something both simple and profound. Due to the expansion of space itself, the separation between us and those distant galaxies is increasing at a rate that exceeds light's ability to bridge the gap. There's no violation of physical law, no cosmic rebellion against the rules of reality, just a beautifully strange interpretation of how space and time can behave in ways our earthbound intuitions don't easily grasp. This cosmic phenomenon has another consequence that's both fascinating and melancholy. There are galaxies we can see today, clear as distant candles through our most powerful telescopes, that have already crossed the event horizon we discussed earlier. They remain visible because the light they emitted long ago is still arriving, still completing journeys that began billions of years in the past. But the newer light these galaxies are producing right now is already beyond our reach. It will never arrive, not even if we wait for periods longer than the current age of the universe. We're seeing the final messages from cosmic correspondents who have already sailed beyond the horizon of communication, their current letters lost forever to the expanding postal system of space itself. It's like watching the taillights of a car that has just turned a corner and disappeared from view. You can still see the glow for a moment, the afterimage of presence, but you know the car is already gone, travelling down roads you'll never follow toward destinations you'll never see. This reality carries a certain peaceful melancholy that somehow feels appropriate for our late-night contemplation. The universe is full of stories we'll never hear in their completion, stars we'll never see born, galaxies we'll never know existed. Not because we lack curiosity or capability, but because the cosmos itself is drawing curtains of expanded space, stretching the stage beyond the reach of even the most patient light. Yet even this limitation is part of the beauty we're exploring together. The fact that we've been able to observe so much of the universe's past is nothing short of miraculous. Despite all the stretching and expansion, despite the cosmic conspiracy of distance and time, we've still managed to see billions of light years in every direction around us. We've caught ancient photons in mid-flight after journeys that lasted longer than Earth has existed. We've read messages that began their journey before our solar system condensed from cosmic dust. We've even detected the faint afterglow of the Big Bang itself, stretched and cooled by expansion, but still detectable as a gentle background warmth that bathes the entire universe. And all of this observation, all this cosmic archaeology, has been accomplished from a tiny planet orbiting an unremarkable star in an average galaxy, in a universe where space itself moves faster than light. It's enough to make you feel simultaneously insignificant and extraordinarily privileged to be here, to be aware, to be part of this vast story that stretches from the smallest quantum fluctuations to the largest structures in the cosmos. As you drift deeper into the contemplation of expanding space, remember that you're not separate from this cosmic growth. The space around you, the space between the atoms in your body, the space that light crosses to travel from these words to your awareness, all of it participates in the gentle, persistent expansion that has been shaping the universe for nearly 14 billion years. You're riding the expansion of space itself, carried along like a passenger on the most patient journey imaginable, surrounded by ancient light and quantum fluctuations and the quiet hum of a universe that has learned, somehow, to grow larger while remaining eternally mysterious. Section 7. The Geometry of Infinity. How space can curve without curving. When we try to imagine the universe, it's natural to picture it like an enormous container, perhaps a vast rectangular box floating in some larger space, with walls and a ceiling and a floor, with edges we might eventually discover if we travelled far enough in any direction. Maybe it extends infinitely in all directions like an endless grid. Maybe it has boundaries somewhere out there in the cosmic distance, marked by signs that read, "End of universe, authorized personnel only." But the real geometry of space is far more subtle and far more fascinating than any simple container could be. As you settle more deeply into your evening's rest, let your mind relax into the possibility that space might not be flat like a tabletop or box-like in its structure. Instead, it might be curved in ways that create realities stranger and more beautiful than any science fiction has dared to imagine. The geometry of the universe isn't just a matter of academic interest or abstract mathematical curiosity. The shape of space has profound implications for how the cosmos evolved, how it behaves on the larger scales, and whether it might one day curve back upon itself in ways that would fundamentally change what we mean when we ask if space ever ends. Let's begin gently with the three main possibilities that emerge from our understanding of cosmic geometry. The first is a flat universe, mathematically speaking, like an infinite sheet of paper or a boundless tabletop extending forever in all directions. In this model, the familiar rules of geometry from high school mathematics apply everywhere. Parallel lines never meet, triangles always add up to 180 degrees, and if you set off travelling in a perfectly straight line, You would continue forever without ever looping back to where you started. The second possibility is what's called a closed universe, shaped something like the three-dimensional equivalent of the surface of a sphere. Here, space curves back upon itself in ways that are difficult to visualize but beautiful to contemplate. If you were to set off in any direction and somehow avoid all the stars and planets and cosmic debris in your path, you would eventually return to your starting point, having travelled in what felt like a straight line but was actually a vast cosmic circle. The third possibility is an open universe, curved like an infinite saddle extending in all directions. In this geometry, parallel lines eventually diverge rather than meeting. Triangles add up to less than 180 degrees, and travelling in a straight line would carry you ever outward into increasingly curved space that never returns to its origin. These shapes, flat, closed, and open, aren't just abstract mathematical concepts. They're tied directly to the universe's density and energy content, to the fundamental question of whether there's enough matter and energy in the cosmos to curve space in particular ways. If the actual density of the universe is greater than what physicists call the critical density, space curves inward upon itself, creating a closed geometry. If the density is less than critical, space curves outward into an open configuration. And if the density matches the critical value exactly, like a cosmic Goldilocks zone of just the right amount of stuff, the universe remains flat. How do we measure something as abstract as the curvature of space itself? The answer lies in studying the cosmic microwave background, that ancient light we discussed earlier that has been travelling since the universe became transparent about 380,000 years after the Big Bang. This primordial glow carries within its subtle fluctuations information about the geometry of the space it has travelled through. By analysing the tiny variations in this ancient light, the slight differences in temperature and intensity across the sky, scientists can determine how space bends photons over cosmic distances. It's like using the pattern of ripples on a lake to understand the shape of the shoreline, or reading the distortion in a photograph to learn about the lens that captured it. So far, all evidence suggests something remarkable, and perhaps unexpected. Our universe appears to be very, very close to perfectly flat. Not absolutely flat, perhaps. The measurements aren't quite that precise, but close enough that any curvature is too subtle to detect with our current instruments. It's like standing on what appears to be an infinite plane that might have a very slight bend somewhere over the cosmic horizon, but as far as we can measure, extends perfectly straight in all directions we can observe. This flatness is both beautiful and puzzling, because it requires an almost impossibly precise balance of matter and energy, a cosmic fine-tuning that seems remarkable in its exactness. If you find your thoughts becoming as flat and peaceful as the space we're describing, let them settle into that gentle state. There's something deeply restful about imagining ourselves living within a cosmic geometry that extends infinitely in all directions without ever turning back upon itself. But here's where the story becomes even more intriguing. A flat universe can still be either infinite or finite in its extent, and a closed universe can be finite in size while still having no boundaries, no edges where you might fall off or encounter cosmic barriers. This idea of finite but unbounded space sounds contradictory at first, like saying you have a box that contains everything but has no walls. But it makes perfect sense once you understand the geometry involved. Consider the surface of our Earth. It's finite. You can measure its total area, but it has no edges. You can walk in any direction forever and never fall off the edge because there is no edge. The surface curves back upon itself so smoothly that every point connects to every other point in a continuous loop. Now imagine taking that concept and extending it to three-dimensional space. That's what cosmologists mean when they talk about a space that's finite but unbounded. It would be like living inside the three-dimensional equivalent of Earth's surface, a space that curves back upon itself so that travelling far enough in any direction would eventually bring you home. In such a universe, you could embark on the ultimate road trip, travelling in a perfectly straight line for billions of years, passing galaxies and cosmic structures beyond counting, and eventually arrive back at Earth from the opposite direction, having circumnavigated the entire cosmos without ever encountering a boundary or barrier. The mathematics of this curved space don't require an outside for the universe to curve into. Space can curve intrinsically, through its own internal geometry, without reference to any larger container or surrounding medium. It's one of the most elegant insights from Einstein's general relativity. Space-time doesn't need to be embedded in something else to have curvature. This intrinsic curvature affects everything that moves through space, including the path of light itself. In curved space, light doesn't travel in straight lines as we normally understand them. Instead, it follows what mathematicians call geodesics, the shortest possible path through whatever geometry it finds itself traversing. On the curved surface of Earth, the equivalent would be great circles like the equator or lines of longitude. In curved cosmic space, light follows similar curved paths, bending and weaving through the geometry of space-time in ways that can create some of the most beautiful phenomena in astronomy. This is why massive objects like stars and black holes can bend light around them, creating what we call gravitational lensing, cosmic funhouse mirrors that distort and magnify the light from objects behind them. When we observe these lensing effects, we're not just seeing individual objects bending light, we're seeing the curvature of space itself made visible. So when we gaze out at the night sky, we're not just seeing objects scattered through flat, empty space. We're seeing a web of light following curved paths through space that might itself be curved, stretched and bent by every massive object it encounters, shaped by the overall geometry of the cosmos. It's like looking at stars through a lens that's constantly shifting and changing, except the distortions aren't flaws in our vision. They're features of reality itself, information about the shape of the space that contains everything we can observe. If the idea of curved space feels too abstract to hold in your mind as sleep begins to call, don't worry about grasping it completely. Sometimes the most profound geometric truths are better experienced as feelings than understood as facts. Let yourself float in the possibility that the universe might be shaped in ways that transcend our everyday experience of shape, that infinity might curve back upon itself in dimensions we can't directly perceive. Whether space is flat, curved inward, or curved outward, we find ourselves living within a geometry that's more beautiful and strange than any architecture humans have ever conceived. We're residents of a cosmic structure that might extend forever, or might loop back upon itself in the most elegant way possible, creating a home for consciousness that's both infinite in its mystery and finite in its perfect completeness. And perhaps that's enough for now, to know that we live within a space whose geometry is still revealing itself to us, still teaching us about the fundamental nature of existence, still surprising us with possibilities that stretch our minds like the universe itself, stretches the light that carries these ideas to your gradually calming awareness. Section 8, the Balloon Universe. Understanding expansion through gentle metaphor. Imagine for a moment that you're a tiny two-dimensional creature living on the surface of a balloon. You can move north, south, east, and west along that curved surface, but you can't dig down into the balloon or float above it. Your entire world, your complete reality, is that flexible skin that curves gently beneath your feet. You don't know that there's a three-dimensional space surrounding your balloon world. You can't perceive the air that fills it or the hands that might be holding it. You simply know that when you walk in what feels like a straight line for long enough, you eventually return to where you started, having somehow completed a journey around your entire universe without ever encountering an edge or falling off. This balloon metaphor has become one of the most helpful ways to understand how our three-dimensional space might behave on cosmic scales, how the universe can expand without expanding into anything, and how space can be finite yet boundless, complete yet endless. As you let your breathing slow to match the gentle pace of cosmic expansion, consider what happens to this balloon universe as it inflates. The balloon doesn't expand into its surroundings. From the perspective of the two-dimensional creatures living on its surface, it simply grows. Distances between points on the surface increase, but there's no external space being invaded or filled. The balloon creates more of itself as it expands, more surface area where there was less before. And from any point on the expanding surface, every other point appears to be moving away, carried by the expansion of the balloon's skin. There's no center to this expansion, no special point from which everything else recedes. Every location is equally valid as a viewpoint from which to observe the universal growth. This captures something essential about how space itself might behave. When cosmologists talk about the expansion of the universe, they don't mean that galaxies are flying outward into some pre-existing void. They mean that space is creating more of itself, stretching in ways that carry galaxies along for the ride, without requiring them to move through space at all. The balloon analogy also helps us understand why there's no center to the universe's expansion. Just as there's no single point on a balloon's surface that could be called the center of expansion, there's no cosmic location that serves as the hub from which everything else is expanding. The Big Bang didn't happen at a particular place in space. It happened everywhere in space simultaneously, and the expansion continues everywhere equally. You could choose any galaxy in the observable universe as your reference point, and from that perspective, all other galaxies would appear to be receding due to expansion. It's a democratic universe in this sense. No location is more special or central than any other. If your thoughts are becoming as round and gentle as the balloon we're imagining, let them curve and settle into that comfortable shape. There's something deeply soothing about imagining the universe as a soft, expanding bubble that grows not through violence or force, but through the patient mathematics of geometry itself. But let's extend this metaphor a bit further and see what else it can teach us about the nature of cosmic space. On our balloon universe, the two-dimensional creatures might notice that light behaves strangely. If they shine a light in what they perceive as a straight line, it would actually follow the curved surface of the balloon, eventually returning to its source if the balloon were perfectly spherical. This is similar to what might happen in our three-dimensional universe if space is curved on cosmic scales. Light from distant galaxies might be following curved paths through space, bent not by individual massive objects, but by the overall curvature of space-time itself. The balloon analogy also illuminates something beautiful about cosmic distances and the expansion of space. As the balloon inflates, dots painted on its surface move farther apart, but the dots themselves don't grow larger. They maintain their size while the distances between them increase. Similarly, in our expanding universe, the spaces between galaxy clusters grow larger over time, but the galaxies themselves, held together by gravity, don't stretch like taffy. Our Milky Way isn't expanding, our solar system isn't growing, and you're not slowly getting taller due to cosmic expansion. The stretching only takes hold in the vast spaces between gravitationally bound structures. What's driving this cosmic inflation? In our balloon metaphor, someone or something is blowing air into the balloon, providing the energy for expansion. In the real universe, we believe that dark energy, that mysterious component we touched on earlier, is playing a similar role, causing space to accelerate in its expansion. It's as if the cosmic balloon is not just being inflated, but is somehow inflating itself faster and faster with each passing moment. We don't understand the mechanism any more than a balloon creature might understand the breath that inflates their world, but we can observe the effects in the behavior of distant galaxies and the stretching of ancient light. This self-accelerating expansion leads to profound questions about the ultimate fate of the universe. If dark energy continues to drive faster and faster expansion, will the cosmic balloon eventually stretch so thin that even the structures we can see today, galaxies, stars, perhaps even atoms themselves, are pulled apart by the growing space between their components? Or might there be some natural limit to expansion, some cosmic feedback mechanism that eventually slows the stretching and allows the universe to settle into a more stable configuration? These questions touch on the deepest mysteries of cosmology and remind us how much we still don't know about the space that contains us. As we contemplate these possibilities, it's worth noting that the balloon analogy, helpful as it is, isn't perfect. Our cosmic balloon isn't floating in some larger space that we can step outside of to observe. Space doesn't need an external framework to curve or expand. It does so according to its own intrinsic properties, its own internal geometry. But the metaphor gives us a way to imagine curved, expanding space that our three-dimensional minds can comfortably hold. It helps us understand how expansion can happen everywhere at once, how space can be finite without having edges, and how the universe can grow without growing into anything external to itself. If you're finding peace in this image of the universe as a gently expanding balloon carrying us all on its surface toward whatever cosmic future awaits, rest in that peace. Let the metaphor work on your imagination as your consciousness settles towards sleep. Sometimes the most important insights about infinity come not from rigorous analysis, but from gentle, metaphorical thinking that allows paradoxes to coexist comfortably in the mind. Whether our universe is truly like a balloon, whether space curves back upon itself or extends infinitely in all directions, we find ourselves riding the expansion of something magnificent and mysterious. Passengers on a journey that began nearly 14 billion years ago and shows no signs of ending anytime soon. And that journey, that gentle stretching of space itself, carries us not toward any destination we can name, but toward the deepest questions about existence itself. Questions about whether infinity is real, whether does space ever end? Section 9, the edges that might not exist. Contemplating boundaries in boundless space. There's something deeply human about searching for edges, for boundaries, for the places where things end and something else begins. We grow up surrounded by walls and fences, by the edges of tables and the boundaries of rooms, by coastlines where ocean meets land and horizons where earth meets sky. Everything in our daily experience seems to stop somewhere, to have limits that define what it is by establishing what it is not. So when we think about the universe, it feels natural, almost inevitable, to imagine that it too must have edges somewhere out there in the cosmic distance. Surely after travelling some truly staggering distance, farther than our most ambitious science fiction has dared to imagine, space must eventually come to an end, like reaching the final room in an impossibly vast mansion, or the edge of an enormous tabletop hanging over some cosmic abyss. But here's where our earthbound intuitions about boundaries begin to mislead us in the most beautiful way. Space, it turns out, doesn't actually need edges to be complete. It can be finite in size without having any boundary at all, and it can be infinite without requiring anything external to contain it. This isn't a limitation of our understanding. It's a feature of cosmic geometry that's more elegant than any boundary-based system we might imagine. Let's start with something familiar, and let your mind rest easy as we explore these ideas. Think about the surface of Earth. If you were to begin walking in any direction, and somehow never encounter obstacles, no mountains to climb, no oceans to cross, no political borders to navigate, you would eventually return to your starting point. You wouldn't fall off anything, you wouldn't hit a wall, and you wouldn't find a sign reading "End of Earth, please turn around." The surface of our planet is finite in area. We can calculate exactly how many square kilometers it contains, but it's also boundaryless. It curves back upon itself in such a smooth, continuous way that there are no edges anywhere to be found. It's what mathematicians call finite but unbounded, a complete surface that nonetheless has no boundaries. Now, if you can hold that idea gently in your mind, as your breathing slows towards sleep, try to imagine extending that concept to three-dimensional space. Picture living inside a cosmic volume that wraps around itself in much the same way that Earth's surface curves back to meet itself. Instead of curving in 2 dimensions like a planetary surface, this space would curve in 3 dimensions, or rather, it would curve through higher dimensional space in ways that our 3-dimensional minds can't easily visualize. From our perspective, living within this 3-dimensional space and unable to step outside of it, everything would feel continuous and endless. We could travel in any direction forever without encountering walls or barriers, but if we could somehow maintain a perfectly straight course for an unimaginably long journey, we might eventually find ourselves back where we started, having circumnavigated the entire universe without ever crossing a boundary. In such a cosmos, galaxies would be like cities scattered across the surface of an enormous sphere, each one unique in its location and properties, but all of them existing within a space that's complete, finite, and boundaryless. There would be no edge to fall off, no cosmic fence to mark the limits of existence, no need to worry about what lies beyond the beyond. This might sound like pure mathematical fantasy, but it's actually a perfectly valid solution to Einstein's equations of general relativity. The geometry is well understood, even if the visualization challenges our 3-dimensional intuitions. Space can curve back upon itself without requiring any external framework to curve into. If your thoughts are becoming as curved and gentle as the space we're describing, let them curve. Sometimes the most important insights about cosmic geometry come not from rigorous mental effort, but from allowing the mind to relax into possibilities that transcend everyday experience. But there are other ways that space might avoid having traditional edges. Consider the possibility that space extends infinitely in all directions, not curved back upon itself, but genuinely endless, like an infinite plane extending forever without repetition or return. In such a universe, there would be no edges because infinity, by definition, has no boundaries. This infinite flatness would mean that space simply goes on forever, containing an endless variety of cosmic structures, an unlimited number of galaxies and stars and worlds, all existing within a geometric framework that never runs out of room. Every journey, no matter how long, would encounter new territories, new configurations of matter and energy, new stories written in starlight across the cosmic dark. The mathematics of infinity suggest that such a universe would contain not just endless variety, but endless repetition as well. With infinite space and only finite ways for matter to arrange itself, every possible configuration would not only exist somewhere, it would exist in infinitely many places, scattered across the boundless cosmic landscape like variations on eternal themes. Yet even infinity, paradoxically, doesn't require edges or external containers. Infinite space doesn't need to be expanding into anything. It's simply infinite, complete in its endlessness, requiring no outside framework to contain or define it. It's like the concept of numbers. You don't need to find the last number to understand that the sequence continues forever. There are other possibilities for edgeless space that emerge from more speculative areas of physics and cosmology. Some theories suggest that our universe might be embedded in higher dimensional space like a vast membrane floating in a cosmic ocean we can't directly perceive. From our perspective, confined to this three-dimensional membrane, space would seem continuous and boundaryless. But from a higher dimensional viewpoint, our entire universe might have edges and boundaries in directions we can't access or observe. This membrane or brain cosmology proposes that we're living on the surface of something larger, like two-dimensional creatures on a balloon who can't perceive the three-dimensional space around their curved world. Our universe might have boundaries in higher dimensions while appearing perfectly continuous and edgeless to us. Still, other theories propose that space might have a cellular or foam-like structure on the larger scales, with our observable universe existing within one cell of an infinite cosmic honeycomb. The boundaries between cells might exist, but they would be so far away that we could never reach them, forever confined to our particular cosmic chamber. These speculative possibilities remind us that edges, if they exist, might not look like anything we're familiar with from our everyday experience. They might not be walls or barriers or places where space simply stops. They might be transitions between different types of space, different physical laws, different cosmic neighborhoods with their own rules and properties. But perhaps the most profound possibility is that space simply doesn't have edges, because edges are human concepts that don't apply to cosmic reality. We search for boundaries because everything in our experience has them, but the universe might operate according to principles that transcend our boundary-based thinking. Maybe space doesn't end because ending is not something that space does. Maybe it doesn't have edges because edges are not something that reality requires. Maybe the question, where does space stop, is like asking, what colour is Wednesday? Or, how much does the number 7 weigh? A category error that assumes space must behave like familiar objects in our daily experience. If you're finding peace in the possibility that space might simply be edgeless by nature, that it might extend or curve or exist without requiring the kinds of boundaries that define objects in our everyday world, rest in that peace. There's something deeply calming about imagining a universe that doesn't need to be contained, that is complete without requiring external definition. The search for cosmic edges might tell us more about the limitations of human cognition than about the actual structure of space. We are creatures evolved to live within bounded environments, rooms and territories and landscapes that have clear limits, so when we venture into cosmology, we naturally bring those expectations with us. But the universe, as we're discovering together on this gentle journey through cosmic mysteries, is under no obligation to conform to our expectations. It might be infinite in ways we can barely imagine, or finite in ways that don't require edges, or structured according to principles so subtle that we haven't yet learned to ask the right questions about them. What we can say with confidence is that space, however it's ultimately organised, is vast enough to hold all our questions about itself. Whether it extends forever or curves back upon itself or exists within frameworks we haven't yet conceived, it provides a home for consciousness, for wonder, for the peaceful contemplation of mysteries that might never be fully resolved. As your awareness drifts between the finite warmth of your immediate surroundings and the infinite possibility that might extend beyond the farthest galaxies, remember that you don't need to solve the puzzle of cosmic boundaries to find meaning in your place within whatever space contains you. Sometimes it's enough to gaze upward into the star-filled darkness and know that you're part of something so vast so mysterious, so beautifully structured that even the question of whether it ever ends opens doorways into wonder that could themselves extend infinitely, like mirrors reflecting mirrors in the gentle darkness of cosmic contemplation. Section 10. The Cosmic Microwave Background. The universe's baby picture. If you could somehow tune your senses to detect the most ancient light still travelling through the universe, you would discover that you're constantly bathed in a gentle glow that has been journeying through space for over 13 billion years. This isn't the dramatic light of stars or the glowing spiral arms of galaxies. It's something far more subtle and far more profound. A soft, uniform warmth that fills every corner of the cosmos like the afterglow of creation itself. This ancient light is called the cosmic microwave background, and it represents the oldest photons that anyone, anywhere in the universe, could possibly observe. It's not just the earliest light we can see, it's the earliest light that exists to be seen, a whisper from the moment when the universe first became transparent to its own illumination. To understand where this primordial glow comes from, we need to journey back in time together, gently, to the universe's infancy. About 13.8 billion years ago, everything that exists today was compressed into a state of unimaginable density and heat. Space, time, matter, and energy all emerged from this condition that physicists call a singularity, a point where our current understanding of physics breaks down and mystery begins. In the universe's earliest moments, space expanded rapidly, spreading energy and matter like cream stirred into coffee, creating more room where there had been no room at all. As the universe grew, it cooled, not quickly like a cup of tea left on a table, but steadily and inevitably, like a cosmic oven slowly reducing its temperature over millions of years. For the first few 100,000 years, the universe was opaque, filled with a plasma of charged particles that scattered light in every direction. Photons couldn't travel very far before being deflected by free electrons and protons, creating a cosmic fog that made the universe impenetrable to its own illumination. It was like trying to see through a dense cloud or thick steam. Light was everywhere, but it couldn't organize itself into the clear images we associate with vision. If you feel your eyelids growing heavy as we contemplate this ancient fog, let them grow heavy. There's something deeply restful about imagining the universe's early opacity, that gentle time when light itself was learning to travel freely through space. Then, about 380,000 years after the Big Bang, something magical happened. The universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, an event that cosmologists poetically call recombination. With fewer charged particles to scatter against, light was suddenly free to travel unimpeded across cosmic distances. The fog lifted. The universe became transparent for the first time. The light that was liberated at that moment, the cosmic microwave background, has been travelling ever since, filling the universe with a faint warm glow that exists everywhere, in every direction, like a cosmic hearth that has never been extinguished. Once a brilliant, searing radiation in the hot young universe, this light has been stretched and cooled by billions of years of cosmic expansion until it now exists as gentle microwaves, invisible to our eyes but detectable by sensitive instruments. This background radiation passes through your room, through your body, through every space between atoms as you rest here contemplating its ancient journey. You are, quite literally, immersed in light that witnessed the universe's transition from opacity to transparency, light that has been travelling since long before our solar system existed, before any of the stars we see in our night sky had formed. We first detected this cosmic afterglow almost by accident, in one of those beautiful moments when the universe reveals its secrets to scientists who weren't specifically looking for them. In the 1960s, two radio astronomers named Arno Penzias and Robert Wilson were using a large horn-shaped antenna to study radio signals from space. They kept detecting a persistent background noise no matter where they pointed their instrument. They cleaned their equipment meticulously, checked their calculations repeatedly, and even removed some pigeons that had been nesting in the antenna, thinking that perhaps these uninvited guests were somehow responsible for the mysterious signal. But the gentle hiss remained, steady and uniform and inexplicably cosmic in its consistency. What they had discovered, without initially realizing its significance, was the afterglow of the Big Bang itself. The cosmic microwave background had been predicted by theory, but this was its first detection, the universe's baby picture captured in the form of ancient radiation that had been travelling since the cosmos was less than 500,000 years old. Since that accidental discovery, scientists have mapped this ancient light in extraordinary detail using space-based observatories designed specifically to study its subtle variations. Missions like COBE, UMAP, and the Planck satellite have given us high-resolution images of this primordial glow, revealing patterns and structures that tell us about the universe when it was younger than a human lifetime. At first glance, the cosmic microwave background appears remarkably uniform, the same temperature and intensity in every direction you might look across the sky. But examine it more closely, with instruments sensitive enough to detect variations of millionths of a degree, and you discover tiny fluctuations scattered across the cosmic sphere, like gentle ripples on an otherwise calm pond. These subtle temperature variations aren't imperfections or noise in the data. They're the seeds of everything. Small differences in density that would grow over billions of years into the galaxies, stars, and planets we observe today. They're fossil imprints of quantum fluctuations from the universe's infancy, tiny random variations that were stretched by cosmic inflation into macroscopic patterns that shape the entire future evolution of cosmic structure. If you think about it, those minute temperature differences in ancient light eventually became the reason you exist. They grew into the dense regions where the first stars formed, where heavy elements were forged in stellar furnaces, where planets eventually condensed from cosmic dust, where life learned to organize itself into increasingly complex forms, and where consciousness eventually emerged to contemplate its own cosmic origins. The cosmic microwave background also carries information about the geometry of space itself. If the universe were curved like a sphere or saddle-shaped rather than flat, those geometric distortions would leave subtle signatures in how the ancient light has travelled to us across billions of years. By measuring the size and distribution of temperature fluctuations in this background radiation, scientists can infer the large-scale curvature of space-time. It's like using the pattern of waves on a lake to understand the shape of the shoreline, or studying the distortion in a photograph to learn about the lens that captured it. So far, all observations point to a universe that is remarkably flat, at least within our ability to measure. Any curvature, if it exists, is so gentle that it's undetectable across the enormous distances we can observe. This flatness has important implications for questions about whether space is infinite. Flat geometries can extend forever without curving back upon themselves. There's something quietly comforting about this ancient light that surrounds us. It's like discovering that the universe has been keeping a gentle nightlight on since its earliest days, a soft background illumination that connects every point in space to the moment when transparency was born and light learned to travel freely. This cosmic glow isn't visible to your eyes as you rest here in the darkness of your evening. It exists at wavelengths that require special instruments to detect, but it's always present, a constant reminder that we live within the expanded and cooled remnant of the universe's fiery youth. If you could somehow tune your vision to see microwave radiation, the night sky would never be dark. Instead of seeing the blackness between stars, you would see a gentle, warm glow everywhere you looked, not bright enough to read by, but bright enough to remind you that space itself carries the memory of its origins. This background radiation also tells us something profound about the uniformity of space on cosmic scales. The fact that it appears nearly identical in every direction suggests that the universe is remarkably homogeneous when viewed from a sufficient distance. Local variations, stars, galaxies, galaxy clusters, are like small perturbations on an otherwise smooth cosmic ocean. This uniformity supports the idea that space might extend far beyond what we can observe, continuing with the same basic properties and structure that we see in our local cosmic neighbourhood. If the universe were fundamentally different in distant regions, we might expect to see variations in the cosmic microwave background that would hint at those differences. As your mind settles into the contemplation of this ancient universal glow, remember that you're not just thinking about distant light or abstract cosmic phenomena. You're considering the actual environment in which you exist, the background radiation that has been a constant presence throughout the entire history of complex matter, the gentle luminescence that has witnessed every star that has ever formed, every planet that has ever cooled, every moment of consciousness that has ever wondered about its place in the cosmos. The cosmic microwave background is like the universe's own meditation, a constant, gentle presence that fills all of space with the memory of beginnings, a soft reminder that even in the apparent emptiness between galaxies, we're never truly alone. The cosmos keeps its own gentle vigil, maintaining this ancient light like an eternal flame that connects every moment to the mystery of how everything began. And as you drift towards sleep surrounded by this invisible but constant cosmic glow, perhaps you can find peace in knowing that the universe has been maintaining this gentle illumination for over 13 billion years, will continue to maintain it long after our sun has cooled and our galaxy has completed many more rotations through the cosmic dark. A patient background warmth that asks nothing from us but offers everything we need to know about our connection to the deepest history of space and time. Section 11. Multiverses and Infinite Possibility. When one universe isn't enough, it's already a significant challenge to contemplate this single universe, with its hundreds of billions of galaxies, its mysterious dark matter and dark energy, its cosmic microwave background, whispering secrets from the universe's infancy, and its space that might curve or stretch into infinity. We have plenty to wonder about, plenty to keep our minds occupied during these quiet hours of nocturnal contemplation. But every now and then, cosmologists and theoretical physicists like to stir the cosmic pot and ask an even more profound question. What if this universe isn't the only one? What if the reality we observe, as vast and mysterious as it appears, is just one bubble in an infinite foam of universes, each with its own laws of physics, its own history, its own possibilities for matter and energy, and perhaps even consciousness? Welcome to the multiverse hypothesis, one of the most fascinating, speculative, and thoroughly mind-bending ideas in modern physics. It suggests, quite simply, that there might be many universes, perhaps infinitely many, each existing in its own cosmic bubble, each telling its own story about how space and time and matter might organize themselves under different conditions. Before we drift too far into these infinite possibilities, let's establish something important. There is currently no direct evidence for the existence of other universes. We haven't detected them, measured them, or received any cosmic postcards from alternate realities. The multiverse remains a theoretical framework, a consequence of certain mathematical models rather than an observed feature of reality. But that doesn't make the idea uninteresting or unworthy of our gentle contemplation as we explore the boundaries of space and possibility. Sometimes the most profound truths about reality emerge first as mathematical possibilities, as theoretical frameworks that help us understand the deeper structures underlying the universe we can observe. There are several different versions of the multiverse hypothesis, each emerging from different areas of physics, and each painting a different picture of how multiple realities might coexist in the cosmic dark. As you let your breathing slow to match the patient rhythm of these vast ideas, we'll explore them one by one, like walking through rooms in an infinite house where each room contains a different version of everything. The first and perhaps most intuitive version is called the bubble multiverse, and it emerges naturally from theories about cosmic inflation, that period of rapid expansion we discussed earlier that occurred just after the Big Bang. According to this model, inflation might not have happened uniformly throughout all of space. Instead, it could have created many separate bubbles, each forming its own universe, each expanding and evolving independently according to its own physical laws. Imagine the early cosmos as a vast pot of boiling water, with bubbles forming and expanding throughout the turbulent medium. Each bubble would be a universe unto itself, with its own space, its own time, its own matter and energy. Some bubbles might be too unstable to support complex structures. Others might have physical constants so different from ours that matter behaves in ways we can't imagine. We happen to live in one of the fortunate bubbles where conditions are just right for stars, planets, and late-night conversations about infinity. In this bubble model, our universe is like a single soap bubble, floating in a cosmic foam. Other bubbles might exist nearby in some higher dimensional sense, but they would be completely separate from ours, forever inaccessible and undetectable, except perhaps through the mathematical frameworks that predict their existence. If you're finding comfort in this image of the cosmos as an infinite bubble bath, where each bubble contains its own complete reality, Let that comfort settle into your bones. There's something beautifully democratic about imagining a multiverse where every possible way of organizing matter and energy gets its own space to unfold and explore its potential. Then there's what's called the quantum multiverse, which emerges from certain interpretations of quantum mechanics, specifically the many worlds interpretation that attempts to resolve some of the paradoxes of quantum behavior. This version suggests that every time a quantum event occurs, every time reality has to choose between multiple possible outcomes, all of those possibilities actually happen, each in its own branching universe. In this quantum multiverse, every decision you've ever made, every random event that has ever influenced your life, every coin flip and dice roll and moment of chance has created branching realities where different outcomes occurred. Somewhere in the infinite garden of quantum possibilities, there's a version of you who chose differently this morning, who woke up to a slightly different world, who made different decisions that rippled outward into alternative histories. This isn't meant to be unsettling or to diminish the significance of your choices and experiences. These alternate versions, if they exist, are completely inaccessible to you. They exist in parallel realities that don't intersect with your own, like stories being written in books you'll never read, in languages you'll never speak. But there's something oddly comforting about the possibility that every potential path your life might have taken is actually being explored somewhere in the vast branching structure of quantum possibility. It suggests that the universe, or multiverse, is large enough to contain not just what is, but everything that could be, every story that could unfold, every possibility that could manifest given the laws of physics and the roll of cosmic dice. The mathematical multiverse proposed by cosmologist Max Tegmark takes this idea even further, suggesting that every mathematically consistent structure exists as a physical reality somewhere in the infinite expanse of possibility. If something can be described by mathematics without logical contradiction, this hypothesis suggests, then it exists as a universe in its own right. This would include not just universes with different particles or forces, but realities with entirely different logical structures, different relationships between space and time, even different forms of mathematics governing the behavior of matter and energy. It's a suggestion so broad and inclusive that it's almost mystical in scope, proposing that mathematics itself is the fabric from which all possible realities are woven. If these ideas of infinite universes feel too vast to hold in your drowsy mind, don't try to hold them. Let them float around your consciousness like gentle dreams, like possibilities that don't demand resolution or complete understanding. Sometimes the most important insights come not from grasping concepts tightly, but from allowing them to exist in the soft space between waking and sleeping thought. Critics rightfully point out that multiverse theories face significant challenges, particularly the problem of testability. If other universes are forever beyond our ability to observe or interact with them, how can we study them scientifically? How do we distinguish between mathematical possibilities and physical realities? These are important questions that remind us to maintain appropriate humility about what we know versus what we might imagine or hope or theorize about cosmic structure. Science works best when it can test predictions against observations, when it can refine theories based on evidence rather than speculation alone. But even if multiverses remain forever theoretical, contemplating them serves important purposes. They stretch our minds, invite intellectual humility, and remind us that reality might be far stranger and more wonderful than even our boldest scientific imagination has yet conceived. The multiverse hypothesis also provides one possible answer to the question of why our universe seems so perfectly suited for the emergence of complexity and consciousness. If there are countless universes with randomly varying physical constants, it's not surprising that we find ourselves in one where the conditions happen to be right for stars, planets, chemistry, and life. It's a cosmic version of what's called the anthropic principle. We observe a universe compatible with our existence because we couldn't exist in universes that were incompatible with consciousness. We're here to ask questions about cosmic fine-tuning because we happen to live in a cosmic bubble where fine-tuning allows questioners to exist. Whether or not multiple universes actually exist beyond our own, pondering them encourages a particular kind of intellectual humility and wonder. It reminds us that even our vast, mysterious, beautiful universe might be just one note in an infinite symphony of realities, just one story being told in and the horizons don't limit our imagination. They frame it, like the borders of a painting that somehow make the artwork more beautiful rather than constraining it. Like the morning sun burning off fog to reveal more of the landscape, every new discovery pushes our cosmic horizons back just a little, revealing more of the vast territory that surrounds our small island of awareness. But some regions will always remain hidden behind the curve of space-time, behind the stretching, swelling boundary where light will never arrive, and perhaps that's as it should be. Perhaps part of the beauty of existence lies in knowing that there are mysteries we'll never solve, territories we'll never map, stories we'll never read to their conclusion. Still, here we are, spinning quietly through space on our small planet, watching photons arrive from billions of years ago, reading the messages they carry about the deep history of everything, and dreaming about what lies beyond the next soft bend in the cosmic road. Even if we can't see it all, even if vast regions of reality remain forever beyond our reach, there's profound beauty in the attempt. In listening to the quiet whispers of ancient light, in following photons to the very edges of the knowable, and in recognizing that while we may never see the complete picture, we're privileged to be part of the story being told across the vastness of space and time. Section 12. The Mystery of Infinite Space. Contemplating endlessness from within, the word infinity has a weight to it that seems almost physical when you speak it aloud in the quiet of evening. It's vast, mysterious, and more than a little overwhelming when you really try to wrap your mind around what it might mean for space to continue forever, without boundary, without end, without any cosmic signpost that might eventually read, "You are here," with an arrow pointing to the edge of everything. Infinity isn't just large. It's a concept that transcends size entirely. It's not like a very long road or an extremely big room. It's something qualitatively different, something that challenges the very foundations of how our minds organize reality. And when we ask whether the universe might be infinite, we're not just asking about cosmic real estate. We're asking about the fundamental nature of existence itself. Let's begin with what we actually know, as opposed to what we might imagine or hope or fear about cosmic infinity. So far, everything we've measured about the large-scale structure of the universe suggests that it could very well be infinite in extent. The cosmic microwave background radiation we discussed earlier, that ancient afterglow of the Big Bang, reveals that space is extremely close to being geometrically flat on cosmic scales. In the context of Einstein's general relativity, a flat universe could easily be infinite in size. If it's not infinite, our current observations suggest it's at least vastly larger than the portion we can observe, many times larger than our 93 billion light-year bubble of cosmic awareness. This brings us back to the relationship between the observable universe and the universe as a whole. Remember, the observable universe is that cosmic sphere around us, containing everything from which light has had time to reach us since the Big Bang. It's an enormous region containing roughly 2 trillion galaxies, but it may represent only an infinitesimal fraction of what's actually out there. Beyond the boundary of our observation, space might simply continue. More galaxies, more cosmic structures, more star-forming regions and black holes and planetary systems, extending outward in every direction without any ultimate boundary or final frontier. It's like standing on a beach and knowing that the ocean continues far beyond the horizon, except in this case, the ocean might literally have no opposite shore. If you feel your mind beginning to stretch uncomfortably as we contemplate true infinity, let it relax. You don't need to contain infinity in your thoughts any more than a single wave needs to contain the entire ocean. Sometimes the most appropriate response to the infinite is simply to rest in its presence, to let yourself be held by the possibility of endlessness rather than trying to grasp it. Here's where infinity becomes both beautiful and strange. We can never actually prove that the universe is infinite, because we're confined to our observational limits. We're like beings living on a vast island who can see only to the horizon, trying to determine whether the ocean around us goes on forever or eventually reaches some distant shore. You can't measure infinity the way you might measure the distance to the nearest city. Infinity isn't a number, it's a concept, an idea about the absence of limits. And in science, concepts need to be supported by evidence, tested against observation, refined through the patient accumulation of data. The evidence we do have suggests that space shows no signs of curving back on itself, or ending abruptly, or behaving in ways that would indicate finite boundaries. As far as we can see in every direction, the universe appears homogeneous and isotropic. The the same basic structure and properties extending as far as our instruments can detect. But as far as we can see is the crucial limitation. We can't directly observe infinity, only look for signs that space continues beyond our current vision without obvious limits or boundaries. It's like trying to determine the size of a forest. While standing among the trees, you can see that it continues in every direction you look, but you can't be certain it doesn't eventually give way to fields or cities or ocean. The idea of an infinite universe brings with it consequences that are both wonderful and slightly unsettling. If space truly extends forever, and if matter is distributed throughout that space in roughly the same patterns we observe locally, then the amount of stuff in the universe, stars, planets, gas clouds, perhaps even life itself, would also be infinite. This means an endless number of stellar nurseries where new stars are being born, an unlimited population of worlds where the chemistry of life might be experimenting with new forms of complexity, an infinite variety of cosmic structures and phenomena that we can barely imagine from our small vantage point in one tiny corner of existence. If you find comfort in this vision of an endlessly creative universe, rest in that comfort. There's something deeply peaceful about imagining a cosmos so vast and so rich that it could contain every possibility, every variation on the themes of matter and energy and consciousness that we observe in our local cosmic neighborhood. But infinity also raises puzzling questions about repetition and uniqueness. In a truly infinite universe, where matter is distributed according to the laws of probability we observe locally, patterns would eventually repeat. Somewhere out there, if the cosmos is genuinely endless, there might be another galaxy very much like our Milky Way, another star system resembling our own, perhaps even another world where someone very much like you is lying in bed at this very moment, listening to words very much like these. This isn't science fiction speculation. It's a mathematical consequence of infinity combined with the finite number of ways that matter and energy can be arranged. Given infinite space and finite possibilities for how atoms can combine, repetition becomes not just likely, but inevitable. The mathematics suggest that if you could travel far enough through infinite space, distances so vast they make our observable universe look like a grain of sand, you might eventually encounter regions where the patterns of matter and energy repeat exactly. Not similar patterns, but identical ones, right down to the last atom, the last photon, the last quantum state. Somewhere in that infinite expanse there might be countless versions of Earth at different stages of development. Somewhere evolution took slightly different paths, where continents formed in different shapes, where different species learned to look up at the stars and wonder about infinity. Others where history unfolded exactly as it has here, where consciousness emerged and began contemplating its own place in the vastness. If this idea feels overwhelming as your mind settles toward rest, remember that such repetitions, even if they exist, would be separated by distances so vast that they might as well exist in entirely separate realities. You'll never encounter your cosmic double, never receive a message from an alternate version of yourself, living in a galaxy identical to our own, but located trillions upon trillions of light years away. The concept of infinite repetition is mathematically fascinating but practically irrelevant to your life, your choices, your relationships, your dreams. It's more like a philosophical puzzle than a practical concern, interesting to contemplate during quiet moments like this, but not something that changes how you experience your daily existence. There's also something beautiful about the possibility that infinity might be real, that the universe might be large enough to contain every story that could possibly be told, every variation on the themes of existence that the laws of physics allow. It transforms the cosmos from something large into something boundless, from something impressive into something that transcends the very concept of size. But we should remain humble about what we don't know. We have only a finite sample of the universe to work with, our observable bubble, and cosmologists remain open to the possibility that space might be very large but still finite, curved back upon itself in ways too subtle for us to detect. The curvature might be so gentle that even light travelling for billions of years doesn't reveal it, like trying to determine the shape of Earth while standing in a small meadow. The curve is there, but it's too gradual to perceive from such a limited vantage point. It's worth noting that even if space is infinite in extent, the universe might still be finite in duration. It had a beginning that we can identify and study, the Big Bang that started cosmic expansion nearly 14 billion years ago. While the notion of a beginning is itself subtle and complex, it suggests that even if the cosmos extends infinitely in space, it hasn't always existed in its current form. This temporal finitude, combined with possible spatial infinity, creates interesting philosophical tensions. How do we understand a reality that might be limitless in extent but limited in age? What does it mean for something infinite to have a birthday? These questions don't have easy answers, and perhaps that's as it should be. Infinity, by its very nature, resists easy categorization or complete understanding. It's meant to be contemplated rather than solved, experienced rather than conquered, appreciated rather than fully grasped. As your consciousness drifts between the finite warmth of your immediate surroundings and the infinite possibility that might extend beyond the farthest stars, let yourself float in that space between knowing and unknowing. The universe, whether infinite or merely very large, is vast enough to hold all your questions, all your wonder, all your peaceful uncertainty about the ultimate nature of space and time. Some ancient thinkers were deeply troubled by the concept of infinity, finding it too strange and unsettling to accept as real. But perhaps they were approaching it with too much urgency, too much need to resolve its paradoxes quickly. Infinity might be better understood as a gentle possibility rather than a problem to be solved, a mystery to be savoured rather than a puzzle to be completed. Whether the universe extends forever or merely appears infinite from our limited perspective, there's something deeply comforting about living within a reality large enough to contain all possibilities, all stories, all the dreams that consciousness has ever dreamed while gazing up at the stars and wondering about its place in the vastness that holds everything. Section 13. The Edge of Knowledge. Where science meets wonder. There comes a moment in every deep exploration of cosmic mysteries when we reach the boundaries not of space itself, but of human knowledge about space. It's a gentle frontier where our instruments fall silent, where our theories become speculative, where the solid ground of scientific certainty gives way to the soft soil of wonder and possibility. This edge of knowledge isn't a failure of science, or a limitation we should feel frustrated about. It's more like reaching the shore of a vast ocean. You can see that the water continues beyond the horizon. You can feel the rhythm of waves that began far offshore, but you can't see the distant continents that might exist beyond your vision. The limitation doesn't diminish the beauty of what you can observe. It enhances it by preserving mystery. As you settle more deeply into your evening's rest, consider how remarkable it is that we've been able to peer as far into space and time as we have. From our tiny planet orbiting an unremarkable star in one galaxy among trillions, we've mapped the cosmic microwave background, discovered the acceleration of cosmic expansion, detected gravitational waves from colliding black holes billions of light years away, and calculated the age and composition of the universe with extraordinary precision. We've learned that space is not the empty stage we once imagined, but an active participant in cosmic evolution. We've discovered that time and space are woven together into a single fabric that can stretch and curve and carry information across vast distances. We've found that even the apparent vacuum between galaxies seethes with quantum activity that maintains the very possibility of existence. Yet for all these remarkable discoveries, the ultimate question of whether space ends remains tantalizingly beyond our reach. Not because we lack curiosity or capability, but because the question itself might transcend the boundaries of what can be answered through observation and measurement. Consider the inherent limitations we face when trying to study the totality of space from within space itself. We're like characters in a novel trying to determine whether their story has a final page, while being unable to step outside the book they inhabit. Every observation we make, every measurement we take, every theory we develop is constrained by our position within the very system we're trying to understand completely. This perspective limitation isn't unique to cosmology. It appears in many areas of human knowledge. We study consciousness using consciousness itself as the instrument of study. We investigate the nature of reality while being embedded within that reality. We explore the foundations of mathematics using mathematical reasoning that assumes those foundations are valid. These recursive loops in human knowledge create both frustration and beauty. Frustration because they prevent us from achieving the kind of absolute external perspective that might resolve our deepest questions definitively. Beauty because they remind us that we're not separate from the mysteries we investigate. We're participants in them, expressions of the very phenomena we're trying to understand. If you feel your thoughts becoming as circular as these epistemological puzzles, let them circle gently without trying to break out of the loop. Sometimes the most peaceful approach to cosmic mysteries is to accept our embedded perspective as a feature rather than a bug, to find comfort in being part of the story rather than needing to read it from outside. The edge of our knowledge about space reveals something profound about the nature of scientific inquiry itself. Science doesn't progress by answering all questions definitively, but by refining our questions, by discovering which mysteries are approachable and which might forever remain beyond our reach, by learning to distinguish between the knowable and the unknowable. This process of approaching the limits of knowledge has its own beauty, its own rhythm that's as patient and persistent as the expansion of space itself. Each generation of scientists pushes the boundary of the known a little farther outward, like explorers mapping an infinite coastline, never expecting to reach the end, but finding meaning in the journey of discovery itself. Recent advances in observational cosmology have pushed our knowledge boundary significantly outward. The James Webb Space Telescope has allowed us to see galaxies forming in the early universe, revealing details about cosmic evolution that were pure speculation just decades ago. Gravitational wave detectors have opened entirely new windows onto cosmic phenomena, allowing us to hear the space-time distortions created by colliding black holes and neutron stars. Yet each advance, each new territory mapped in our cosmic understanding, reveals new mysteries, new questions, new regions beyond our current reach. It's like climbing a mountain and discovering that each summit reveals previously hidden peaks, stretching toward horizons you hadn't even known existed. This expanding frontier of cosmic knowledge suggests that the universe might be fundamentally inexhaustible in its mystery, not because it's trying to hide its secrets from us, but because the questions we can ask about reality are themselves infinite in their depth and complexity. The question of whether space ends might be one of those eternal questions that doesn't have a final answer, but instead has an infinite series of better and better approximations, deeper and deeper insights, more and more refined ways of thinking about the relationship between finite observers and infinite possibilities. There's something peaceful about accepting this open-endedness, about embracing our role as finite beings contemplating infinite possibilities. We don't need to solve the mystery of cosmic boundaries to participate meaningfully in the cosmic story. We don't need to reach the edge of space to find our place within the vastness that contains us. Perhaps the most important discovery we've made about space is not whether it ends, but how it connects everything within it. Space doesn't separate objects. It relates them to each other through gravity, through the shared history of cosmic expansion, through the quantum fields that fill every region and connect every particle to every other particle, through subtle but fundamental interactions. In this view, asking whether space ends becomes less important than appreciating how space unifies everything within it. Whether infinite or finite, whether curved or flat, whether unique or one among countless multiverses, space serves as the medium through which matter and energy and consciousness discover their relationships to each other and to the whole. As your awareness drifts between the certainties of scientific knowledge and the vast uncertainties that stretch beyond our current understanding, remember that uncertainty itself is not emptiness. Like the quantum vacuum, uncertainty is full of potential, pregnant with possibilities, alive with questions that might lead to insights we can't yet imagine. The edge of knowledge is not a wall that stops our exploration. It's a horizon that invites continued journey, a reminder that the universe is patient enough to reveal its secrets gradually, over generations of human curiosity and wonder and late-night contemplation under star-filled skies. And you, resting here in your small corner of space and time, are part of that ongoing exploration. Your capacity for wonder, your willingness to contemplate mysteries that might never be fully resolved, your peaceful acceptance of uncertainty as a feature rather than a flaw of cosmic existence. All of this participates in the universe's long conversation with itself about its own nature and possibilities. Section 14, Domain Walls and Cosmic Boundaries. When space changes its rules, deep in the theoretical territories of modern physics, beyond the comfortable boundaries of well-established science, there exist possibilities for cosmic boundaries that are stranger and more subtle than any edge or wall we might imagine from our everyday experience. These aren't boundaries where space simply stops, but transition zones where the fundamental rules of reality might shift, where the very laws of physics could change like seasons transitioning from summer to winter. Imagine, as you settle into the peaceful rhythm of late-night contemplation, that space isn't uniform in its properties throughout its vast extent. Picture instead a cosmic landscape where different regions operate according to slightly different versions of physical law, separated by boundaries so subtle that light can cross them without difficulty, but where the underlying nature of matter and energy might be fundamentally altered. These theoretical structures are called domain walls, and they represent one of the most exotic possibilities for how space might be organized on the larger scales. They emerge from certain theories about how the universe cooled and organized itself in its earliest moments, when the fundamental forces that govern reality were settling into their current configurations. Think of how water freezes into ice crystals. The transition doesn't happen uniformly throughout a body of water. Instead, crystallization begins at many different points simultaneously, with each growing region developing its own crystal structure. The boundaries between these regions, where different crystal orientations meet, create interfaces that persist within the solid ice. Domain walls represent a similar concept applied to the fabric of space-time itself. During the universe's early cooling, space might have undergone phase transitions where different regions crystallized into slightly different configurations of physical law. The boundaries between these regions would form cosmic domain walls, immense structures stretching across space marking the transition zones between different versions of reality. If such walls exist, they would represent boundaries not in space, but in the rules that govern space. Crossing a domain wall might be like stepping from one cosmic jurisdiction into another, where gravity might be slightly stronger or weaker, where electromagnetic forces might behave differently, where the very particles that make up matter might have different masses or properties. Most theoretical models suggest that any domain walls formed in the early universe would have quickly disappeared or been diluted to irrelevance by cosmic expansion. But some speculative scenarios imagine they could persist, lurking in the cosmic deep like invisible membranes that separate different provinces of physical law. If you encounter a domain wall during some impossible future journey across the cosmos, the experience might be surprisingly undramatic. You might pass through without noticing anything unusual at first. But gradually, you might observe that the stars in this new region of space behave slightly differently, that the chemistry of matter follows subtly altered rules, that the fundamental constants that define how energy and matter interact have shifted by small but detectable amounts. It would be like travelling to a country where the language is almost identical to your own, but where certain words have slightly different meanings, where the grammar follows subtly different rules. You could communicate and function, but you would gradually realize that you're in a fundamentally different linguistic universe. These cosmic boundaries represent one way that space could have organization and structure without having traditional edges. Instead of asking whether space ends, we might ask whether space ever changes its fundamental character, whether the properties we observe locally persist throughout all of cosmic space, or whether there are regions where reality operates according to different principles. Another type of cosmic boundary emerges from theories about cosmic inflation and the formation of bubble universes we discussed earlier. If our universe is indeed one bubble in an infinite foam of expanding space, then the boundary of our bubble would represent a real edge, not of space itself, but of the region where space operates according to the physical laws we observe. Beyond such a boundary, space might continue, but it might be space organized according to entirely different principles, where matter and energy and time itself might behave in ways so foreign that we wouldn't recognize them as physics at all. These boundaries wouldn't be walls that stop expansion or prevent travel. They would be transition zones where one type of space gives way to another. If your mind is finding peace in these subtle distinctions between different types of cosmic boundaries, rest in that peace. The universe appears to be endlessly creative in the ways it might organize itself, endlessly generous in providing possibilities for existence that transcend our earthbound experience of how things usually work. Some theoretical models propose that space might have a cellular structure on scales so vast that even our observable universe represents only a tiny fraction of a single cosmic cell. These cells might be separated by boundaries that exist in dimensions we can't access directly, creating a kind of cosmic honeycomb where each cell contains its own complete universe with its own history and possibilities. In such a structure, asking whether space ends becomes like asking whether a honeycomb ends. The answer depends on whether you're talking about individual cells or the structure as a whole. Each cell might be finite and complete in itself, while the overall structure could extend infinitely in dimensions we can't perceive. The beauty of these speculative boundaries lies not in their likelihood. Most remain highly theoretical and may forever remain untestable, but in how they stretch our imagination and remind us that reality might be far stranger and more richly structured than even our boldest scientific theories currently suggest. They also provide a gentle reminder that the absence of detectable boundaries in our local cosmic neighbourhood doesn't necessarily mean that space is uniform and unchanging throughout its entire extent. The universe might be far more varied and complex in its large-scale organisation than we can currently observe or imagine. As we explore these possibilities together, it's important to maintain the kind of intellectual humility that makes for good science and peaceful contemplation. These domain walls and phase boundaries and cosmic cellular structures remain largely speculative, emerging from mathematical models rather than direct observation. They represent the frontier where science shades into philosophy, where rigorous mathematical reasoning encounters the fundamental limitations of what can be tested and verified through empirical investigation. This frontier is not a weakness of science, but one of its greatest strengths. The willingness to acknowledge what we don't know while continuing to push gently against the boundaries of the knowable. Whether space has subtle boundaries that separate regions with different physical properties, whether our universe is one cell in a cosmic honeycomb, whether domain walls stretch across the cosmos separating different versions of reality, these possibilities remind us that the question, does space ever end, might have answers more beautiful and strange than simple yes or no. Space might not end so much as transform, not stop so much as change its character, not conclude so much as transition into forms of existence so different from what we know that they challenge our very concepts of space, and ending, and boundary, and infinity. And you, resting here in your small region of space where the laws of physics behave in the familiar ways that make your existence possible, are participating in cosmic mysteries that stretch far beyond what any mind can fully encompass. Whether space ends or continues, whether it changes or remains constant, whether it's simple or unimaginably complex in its deeper structure, you're here within it, conscious of it, connected to it in ways that make you part of the story it's telling about itself. Section 15, the holographic principle. When reality lives on the surface, as you rest in the gentle darkness of your evening, contemplating the vast three-dimensional space that seems to surround you in every direction, prepare your mind for one of the most beautiful and strange ideas that modern physics has discovered about the nature of reality itself. What if everything you perceive as existing in three-dimensional space, every star, every galaxy, every atom in your body, is actually information encoded on a distant two-dimensional surface, like a cosmic hologram of unimaginable sophistication? This isn't science fiction speculation or mystical thinking. This is the holographic principle, a profound insight that emerges from our best current theories about black holes, quantum mechanics, and the fundamental nature of information in the universe. It suggests that the three-dimensional reality we experience might be a kind of projection, a remarkably detailed image created by information stored on the boundary of space itself. The idea first emerged from studies of black holes, those cosmic graveyards where matter disappears behind event horizons that seem to cut them off from the rest of the universe forever. But physicist Stephen Hawking discovered that black holes aren't completely black. They emit radiation, slowly evaporating over cosmic timescales, returning their mass and energy to the surrounding space. This created a puzzle that seemed to threaten the fundamental laws of physics. If information falling into a black hole disappears forever when the black hole evaporates, it would violate one of the most basic principles of quantum mechanics, that information cannot be destroyed, only transformed or relocated. The resolution to this puzzle led to a remarkable insight. Perhaps the information that falls into a black hole isn't actually destroyed or lost inside the black hole's interior. Instead, it might be encoded on the black hole's surface, its event horizon, like information stored on a vast spherical hard drive. From this perspective, The three-dimensional interior of a black hole might be less fundamental than the two-dimensional information encoded on its surface. The interior might be, in some sense, a holographic projection of the information stored on the boundary. If you find your mind beginning to stretch as we explore these ideas, let it stretch gently. Sometimes the most profound insights about reality require us to temporarily set aside our intuitive assumptions about how space and information and existence might be organized. This holographic thinking, initially developed for black holes, has been extended to the universe as a whole through what's called the ADS/CFT correspondence, a mathematical relationship that suggests certain types of space-time geometry might be equivalent to information processing on their boundaries. In the most extreme version of the holographic principle, everything we observe in our three-dimensional universe, the motion of planets, the nuclear fusion in stellar cores, the chemical processes in your brain that create consciousness itself, might be the three-dimensional shadow of information processing occurring on a two-dimensional surface at the edge of cosmic space. This boundary wouldn't be a wall or barrier in any conventional sense. It would be more like the surface of a cosmic hard drive, storing and processing the information that manifests as our three-dimensional reality. We wouldn't be able to travel to this boundary or interact with it directly, any more than characters in a holographic projection could reach out and touch the holographic plate that creates their image. The holographic principle suggests a radically different answer to the question of whether space ends. Instead of asking whether there's a place where space stops, we might ask whether the apparent three-dimensional extension of space is fundamental, or whether it emerges from more basic two-dimensional information processing. In this view, space doesn't need to end because space, as we experience it, might not be the most fundamental level of reality. The true substance of existence might be information organized on surfaces, with what we perceive as three-dimensional space being a kind of user interface, a way of experiencing and interacting with underlying information structures. This connects to something even more profound about the relationship between consciousness and cosmic structure. If our three-dimensional reality emerges from information processing on cosmic boundaries, then consciousness itself, your ability to think these thoughts, to wonder about infinity, to rest peacefully while contemplating the deepest mysteries of existence, might be information processing occurring at the interface between different levels of cosmic organization. You wouldn't be a separate observer looking out at the universe from some external vantage point. You would be the universe processing information about itself, space and time organizing themselves temporarily into awareness, the cosmic hologram becoming conscious of its own projection. If these ideas feel too abstract to hold in your drowsy mind, don't worry about understanding them completely. The holographic principle is still highly speculative, still being developed and debated by physicists who are themselves uncertain about its ultimate implications. What matters for our gentle exploration is not whether the principle is correct, but what it suggests about the possible richness and strangeness of cosmic reality. It reminds us that space might be organized in ways that transcend our three-dimensional intuitions, that the question of cosmic boundaries might not be about walls or edges, but about the relationship between information and the apparent space that information creates or projects. The holographic principle also suggests that the universe might be far more economical in its use of information than we might expect. If three-dimensional reality can be completely encoded on two-dimensional surfaces, it means that the cosmos might be able to contain infinite complexity and detail using finite amounts of fundamental information. This economy of cosmic information processing offers another perspective on the question of whether space ends. Instead of requiring infinite space to contain infinite possibilities, a holographic universe might contain boundless complexity within bounded information processing systems. As you drift towards sleep while contemplating these possibilities, remember that whether reality is fundamentally three-dimensional as it appears, or emerges from two-dimensional information processing as the holographic principle suggests, you are an integral part of whatever information processing system creates and maintains cosmic reality. Your consciousness, your dreams, your peaceful contemplation of infinity, all of this represents the universe exploring its own possibilities, reality investigating its own nature, the cosmic information system becoming aware of itself through the temporary arrangement of matter and energy that you represent. Whether space ends at boundaries we haven't discovered, whether it transforms into different types of information processing, or whether it continues infinitely with consistent properties throughout. You're here within it, part of it, connected to it in ways that make your existence a cosmic event rather than an isolated accident. The holographic principle, whether ultimately correct or not, reminds us that reality might be far more interconnected, far more unified, and far more mysteriously organized than our everyday experience suggests. We might not just live in space, we might be expressions of space, ways that cosmic information organizes itself into awareness and wonder, and the gentle contemplation of its own infinite possibilities. Section 16. The Eternal Recurrence. Cycles in infinite space. In the quiet of your evening, as your mind drifts between sleep and waking contemplation of cosmic mysteries, consider a possibility that is both ancient and utterly modern, both philosophical and deeply scientific. The idea that space and time might be organized not as a straight line extending infinitely into an unknown future, but as a vast cycle that eventually returns to its beginning, like a cosmic breath that expands and contracts in rhythms so slow that they encompass the entire history of stars and galaxies and consciousness itself. This concept of cosmic recurrence has appeared in various forms throughout human thought, from ancient philosophers who imagined eternal cycles of creation and destruction, to modern cosmologists who study the mathematical possibilities for how the universe's expansion might eventually reverse itself. It's an idea that transforms our understanding of endings and beginnings, suggesting that what we call the end of space might actually be its return to a new beginning. Let's explore this gently, allowing the mathematics and philosophy to blend like twilight colours in the evening sky. If the universe is finite but unbounded, curved back upon itself like the surface of a sphere, then space doesn't end in the sense of reaching a final boundary. Instead, it completes itself, forming a closed loop that contains all of existence within a perfect, seamless whole. But there's another kind of recurrence that might operate on even grander scales, involving not just the geometry of space but the evolution of time itself. Some cosmological models suggest that the universe's current expansion might eventually slow, stop, and reverse, leading to a contraction phase that would eventually compress all of space back into conditions similar to those that existed just after the Big Bang. This scenario, sometimes called the Big Crunch, would represent a kind of cosmic death and rebirth, an ending that is simultaneously a beginning. Space wouldn't disappear or encounter an external boundary. It would instead collapse back into the primordial state from which it originally emerged, potentially setting the stage for a new cycle of expansion and cosmic evolution. If you feel your thoughts becoming as cyclical as the cosmic processes we're contemplating, let them cycle peacefully. There's something deeply restful about imagining time and space as part of an eternal rhythm rather than a linear journey towards some ultimate destination or termination. In such a cyclical universe, the question of whether space ends becomes transformed into a question about whether cosmic cycles end. Does each cycle repeat the previous one exactly, like a cosmic recording playing the same song infinitely? Or does each new cycle explore different possibilities, like an improvisation on eternal themes? Some versions of cyclical cosmology suggest that each new universe might be slightly different from its predecessors, that the fundamental constants of physics might vary slightly from cycle to cycle, creating an infinite exploration of cosmic possibilities across infinite time. In this view, our current universe would be just one movement in an eternal symphony, one iteration in an endless series of cosmic experiments. The mathematical elegance of cyclical models lies in how they resolve the question of ultimate origins. Instead of requiring a first moment of creation from nothing, cyclical cosmology suggests that the universe has always existed in one form or another, alternating between phases of expansion and contraction, between complexity and simplicity, between the three-dimensional space we know and the compressed singularity from which it emerges and to which it returns. But current observations of cosmic acceleration driven by dark energy suggest that we may not live in a cyclical universe. If dark energy continues to drive faster and faster expansion, the universe appears destined for continued growth rather than eventual collapse. The cosmic cycles, if they exist, might operate on scales or in ways that transcend our current understanding of dark energy and cosmic evolution. There are also quantum mechanical versions of eternal recurrence that operate on entirely different principles, In an infinite universe with finite possible arrangements of matter and energy, the laws of probability suggest that every possible configuration would not only occur somewhere, it would occur infinitely many times, scattered across the endless expanse of space. This quantum recurrence wouldn't require cosmic cycles or collapsing space. Instead, it would emerge naturally from the mathematics of infinity, combined with the finite number of ways that atoms and energy can arrange themselves. Given unlimited space and unlimited time, every possible moment, every possible experience, every possible arrangement of matter would repeat infinitely throughout the cosmic expanse. Somewhere in that infinite space, there might be regions where matter has organized itself into exactly the same patterns we observe in our local cosmic neighborhood. Not similar patterns, but identical ones, right down to the last photon, the last quantum state, the last neural firing in brains identical to your own. If this idea of infinite repetition feels overwhelming as your consciousness settles toward rest, remember that such repetitions would be separated by distances so vast that they might as well exist in separate realities. The practical significance of these quantum twins scattered across infinity is essentially zero. They don't affect your daily life, your choices, your relationships, or your dreams any more than identical snowflakes falling in different centuries affect each other. But there's something oddly comforting about the possibility that the universe might be large enough and patient enough to explore every possibility that the laws of physics allow. It suggests a cosmos that's not just vast in its extent, but infinite in its creativity, endlessly experimenting with new ways of organizing matter and energy and consciousness into novel forms of beauty and complexity. The concept of eternal recurrence also offers a different perspective on the meaning and significance of individual existence. If every possible life is lived infinitely many times across infinite space, does that make each particular instance less meaningful? Or does it suggest that meaning itself might be one of the fundamental features of cosmic organization? Perhaps the significance of consciousness doesn't depend on its rarity or uniqueness, but on its capacity to participate in the universe's ongoing exploration of its own possibilities. Whether you're the only version of your consciousness or one of infinitely many, you're still here now, still capable of wonder, still participating in the cosmic conversation about the nature of space and time and existence. As your awareness drifts between these vast possibilities, cyclical time, quantum recurrence, infinite repetition across boundless space, let yourself find peace in the mystery rather than anxiety about the ultimate nature of cosmic organization. Whether the universe cycles or extends infinitely, whether consciousness is rare or abundant across the cosmic expanse, whether space ends or continues forever, you are here now, experiencing this moment of connection to the deepest questions about reality. And that experience, that capacity for wonder and contemplation and peaceful acceptance of cosmic mystery, is remarkable whether it occurs once in a finite universe or infinitely many times across eternal space. You are space and time organizing themselves temporarily into awareness, the cosmos becoming conscious of its own beauty and mystery through the gentle filter of your drowsy contemplation of infinite possibilities. Section 17. The temperature of emptiness. How space remembers its origins. Even in the most remote regions of the universe, in the vast spaces between galaxy clusters where darkness reigns for hundreds of millions of light years in every direction, space isn't quite as cold as you might imagine. Those seemingly empty regions, which appear to contain nothing but vacuum and the gentle passage of ancient light, maintain a temperature that tells one of the most beautiful stories in all of cosmology. Space itself has a memory, encoded in the form of heat, a gentle warmth that pervades every cubic centimetre of the cosmos, from the densest stellar cores to the most isolated voids between superclusters. This background temperature isn't much, only about 2.7 degrees above absolute zero, but it represents something profound about the nature of space and its relationship to cosmic history. As you settle into the peaceful contemplation of cosmic temperature, imagine the universe as, whether our universe is truly like a balloon, whether space curves back upon itself or extends infinitely in all directions, we find ourselves riding the expansion of something magnificent and mysterious, passengers on a journey that began nearly 14 billion years ago and shows no signs of ending anytime soon. And that journey, that gentle stretching of space itself, carries us not toward any destination we can name, but toward the deepest questions about existence itself. Questions about whether infinity is real, whether space ever truly ends, and what it might mean to live within a cosmos that could be both finite and boundless at the same time. Section 18, Quantum Foam and the Smallest Scales. Where space dissolves into possibility, as your consciousness drifts deeper into the gentle territory between waking and sleeping, let's journey together to the smallest possible scales of reality, to distances so tiny that they make atoms look like galaxies, where the very concept of space as a smooth, continuous fabric begins to dissolve into something more fundamental and far stranger. At these scales, called the Planck length, about 10 to the negative 35th meters, space itself might not be the smooth geometric entity we experience in our everyday world. Instead, it might be a constantly fluctuating foam of quantum possibilities, where the ordinary rules of geometry break down and reality becomes a probabilistic dance of virtual particles appearing and disappearing faster than time itself can measure. Imagine the surface of the ocean viewed from an airplane. From high altitude, the water appears smooth and continuous, a perfect blue plane extending to the horizon. But descend closer, and you begin to see waves. Closer still, and you notice ripples and foam where waves break. Get close enough, and the surface reveals itself to be anything but smooth. It's a constantly changing texture of motion and energy, never the same from moment to moment. Quantum foam represents a similar idea applied to the fabric of space-time itself. At the scales we can observe directly, space appears smooth and continuous. But at the Planck scale, space might reveal itself to be a seething foam of quantum fluctuations, where the very concepts of distance and direction and dimensionality become uncertain, probabilistic, subject to the strange rules of quantum mechanics that govern reality at its most fundamental level. This quantum foam isn't just a theoretical curiosity, it might be the most basic level of reality, the substrate from which everything else emerges. The smooth space-time of general relativity, the particles and fields of quantum mechanics, the stars and galaxies of astronomy, all of it might be emergent properties of deeper quantum processes occurring at scales too small to observe directly. If your thoughts are becoming as foam-like as the space we're contemplating, let them bubble and dissolve peacefully. There's something deeply restful about imagining reality as a constant process of creation and dissolution, a cosmic tide that ebbs and flows at the deepest levels of existence. At these quantum scales, the question of whether space ends takes on entirely new meaning. If space is fundamentally discontinuous, made of discrete quantum units that appear and disappear according to probabilistic laws, then asking whether space ends might be like asking whether a collection of soap bubbles ends. Each individual bubble is finite, but the foam as a whole might extend indefinitely. Some theories of quantum gravity suggest that space and time themselves emerge from more fundamental quantum processes, like the way temperature emerges from the motion of molecules. In this view, space isn't a stage where quantum events occur. Space is what quantum events create when they organize themselves in particular ways. This emergence of space-time from quantum processes offers a radically different perspective on cosmic boundaries. Instead of looking for places where space stops, we might look for places where the quantum processes that create space change their character, where different types of quantum organization give rise to different types of space-time geometry. The mathematical frameworks that describe quantum foam suggest that it might be self-organizing in ways that create natural length scales, natural boundaries between different regimes of quantum behavior. These boundaries wouldn't be walls or barriers in any conventional sense. They would be transition zones where quantum processes shift from one mode of organization to another. Recent developments in string theory and loop quantum gravity have provided increasingly sophisticated models of how space might be constructed from quantum building blocks. These theories suggest that what we experience as continuous spacetime might be an emergent property of underlying discrete structures, like the way a smooth curve emerges from a collection of individual pixels in a high-resolution digital image. If space is indeed constructed from quantum foam, then its apparent smoothness at large scales would be similar to how a photograph appears continuous and smooth when viewed from a normal distance, even though it's actually composed of discrete pixels that become apparent only when examined closely enough. This pixel-like structure of space might provide natural cutoffs or boundaries for physical processes. Just as digital images have finite resolution, beyond which no additional detail can be stored or displayed, quantum foam might provide natural limits to how much information can be packed into any given region of space, how complex structures can become, how precisely locations can be defined. These quantum limitations might represent the deepest level of cosmic boundaries, not boundaries where space ends, but boundaries built into the very structure of space that determine how space can behave, what kinds of processes it can support, what types of information it can store and transmit. The study of quantum foam also connects to some of the most speculative ideas about cosmic boundaries and the multiverse. If space is constructed from quantum processes, then different types of quantum organization might give rise to entirely different types of spacetime, different cosmic bubbles with their own emergent properties and physical laws. The boundaries between such quantum domains wouldn't be detectable through ordinary observation. They would exist at scales far smaller than anything we can currently probe experimentally. But they might determine the large-scale properties of cosmic regions, creating a kind of quantum geography where different neighborhoods of the multiverse operate according to different emergent rules. As your mind settles into the contemplation of these quantum possibilities, remember that these ideas, however speculative, emerge from our best current understanding of how reality works at its most fundamental levels. Quantum mechanics isn't just a theory about small particles, it's a framework for understanding how information and possibility organize themselves into the experience of existence. You are, in a very real sense, an emergent property of quantum foam, a temporary pattern in the quantum processes that create and maintain space-time. Your consciousness, your capacity for wonder, your peaceful contemplation of cosmic mysteries, all of this emerges from quantum processes occurring at scales so small that they predate and underlie every particle in your body, every thought in your mind, every breath you take as you drift towards sleep. The quantum foam that might constitute space at its deepest level is the same quantum foam that maintains your existence from moment to moment. You don't just live in space. You are a way that space has learned to organize itself into awareness, a temporary intensification of the quantum processes that create cosmic reality. If space is indeed quantum foam all the way down to its foundations, then asking whether space ends becomes a question about whether quantum processes end, whether the fundamental creative activity of reality ever finds a place where it stops operating, where possibility stops manifesting as actuality. And perhaps that's the most beautiful insight of all. Space might not end because space is not a thing that could end. It's the ongoing process of reality creating itself, the universe's way of maintaining the possibility that consciousness like yours could emerge and contemplate the mystery of its own existence within the gentle foam of quantum space-time. Section 19. The information content of space. How much can infinity hold? In the peaceful quiet of your evening contemplation, as your mind drifts between the finite warmth of your immediate surroundings and the infinite possibilities we've been exploring together, consider one of the most subtle and profound questions that emerges from our investigation of cosmic boundaries. Not just whether space ends, but how much information space can contain, how much complexity and detail and story can be written in the cosmic medium that holds everything. This question of cosmic information storage connects to some of the deepest mysteries in modern physics, linking quantum mechanics to cosmology, consciousness to geometry, and the practical limits of computation to the ultimate structure of reality itself. It's a question that transforms our inquiry from "does space end?" to "what are the limits of what space can remember, store, and process?" Let's begin with something familiar and let your breathing slow as we explore these ideas. Every book ever written, every song ever composed, every digital photograph ever taken, every moment of video ever recorded, all of these represent information, patterns of organization that carry meaning and can be stored, transmitted, and retrieved. Your brain itself is an information storage device, maintaining memories, processing new experiences, creating the stream of consciousness that allows you to contemplate these cosmic questions. Now imagine trying to determine how much total information could be stored in a given volume of space. At first, you might think the answer is infinite. If space is continuous and smooth, couldn't you encode information at arbitrarily small scales, storing unlimited amounts of data in any finite volume? But quantum mechanics suggests otherwise. At the smallest scales of reality, information storage is limited by what's called the Planck scale, those fundamental quantum units where space itself becomes discrete rather than continuous. These quantum limitations create natural boundaries for how much information can be packed into any region of space, no matter how clever our encoding schemes might become. The mathematics of quantum information theory suggests that the maximum amount of information that can be contained in any spherical region of space is proportional not to the volume of that sphere, but to the area of its surface. This is called the Bekenstein bound, and it implies that space has finite information storage capacity even when its volume is arbitrarily large. Think of it this way. If you wanted to store the maximum possible amount of information in your room, quantum mechanics suggests that the limit would be determined not by how you fill the three-dimensional space inside the room, but by how much information you could encode on the room's walls, ceiling, and floor. The storage capacity is fundamentally two-dimensional, not three-dimensional. This connects back to the holographic principle we explored earlier, suggesting that the information content of any region of space might be encoded on its boundary rather than distributed throughout its volume. It implies that three-dimensional space might be a kind of projection or interface, a way of experiencing and interacting with more fundamental two-dimensional information processing. If you find these ideas of cosmic information limits too complex to follow as your mind settles toward rest, don't worry about grasping every detail. Sometimes the most important insights come not from understanding technical details, but from appreciating the broader implications. In this case, the realization that space itself might have limits not in its extent, but in its capacity to store and process information. These quantum limits on information storage might represent the deepest level of cosmic boundaries, not places where space stops, but limits on what space can do, constraints on how complex the patterns within space can become, natural cutoffs that prevent infinite information density from creating paradoxes or contradictions in the structure of reality. The Bekenstein bound also connects to fascinating questions about the relationship between consciousness and cosmic information processing. If your brain is an information processing system, and if space itself has limits on information processing, then consciousness might represent a particularly efficient way that the universe has learned to organize information within the constraints imposed by quantum mechanics. Your ability to think about infinity, to contemplate cosmic boundaries, to wonder about the ultimate nature of space, all of this represents information processing occurring within the quantum limits that govern cosmic reality. You are space exploring its own information processing capabilities, the universe investigating the limits of its own computational power through the medium of conscious awareness. Recent developments in quantum information theory have revealed even more subtle connections between information, space, and the question of cosmic boundaries. Some theories suggest that space itself might be emergent from more fundamental information processing, that what we experience as geometric relationships between objects might actually be information relationships between quantum systems. In this view, distance itself might be a measure of how much information is required to correlate the quantum states of objects separated in space. Objects that are close together in space are strongly correlated informationally, while objects that are far apart require more information to maintain their correlations across the intervening distance. This information-theoretic view of space suggests that cosmic boundaries, if they exist, might be determined by information processing limits rather than geometric constraints. Space might end not by reaching a wall or edge, but by reaching the limits of how much information can be coherently processed within a single cosmic system. These limits might create natural domains within space, regions where information can be coherently organized and processed, separated by boundaries where information correlations break down and different cosmic domains begin. Such boundaries would be invisible to direct observation, but fundamental to the organization of reality itself. The connection between information and space also provides a new perspective on the question of cosmic infinity. An infinite universe might require infinite information to describe completely, but quantum mechanics suggests that information is always finite, always constrained by the discrete nature of quantum processes. This tension between infinite space and finite information might be resolved in various ways. Perhaps infinite space contains infinite repetition of finite information patterns, like an infinitely long book that tells the same stories over and over again in different cosmic neighborhoods. Or perhaps the universe is finite in its information content while appearing infinite from the perspective of any local observer embedded within it. As your consciousness drifts between these technical possibilities and the peaceful darkness of your evening, remember that you don't need to resolve these information paradoxes to participate meaningfully in cosmic reality. Whether space is infinite in extent or finite in information content, whether consciousness is rare or abundant across cosmic domains, you are here now, processing information about the deepest mysteries of existence. Your brain, working within the quantum limits that govern all information processing, is currently engaged in one of the most remarkable computational tasks possible, contemplating infinity itself, using finite neural resources to explore questions about boundless possibilities, creating temporary patterns of information that correspond to concepts like endlessness and eternity and the ultimate nature of space. This represents space achieving one of its most sophisticated organizational possibilities, matter and energy arranging themselves into systems capable of contemplating the very framework that contains them. You are cosmic information processing, exploring its own limits, space investigating its own nature through the gentle medium of consciousness resting peacefully in the darkness of infinite possibility. Section 20. The Music of the Spheres. Cosmic harmonies in infinite space. As we drift deeper into our exploration of cosmic boundaries and infinite possibilities, let your mind rest on one of the most beautiful metaphors that has ever been applied to the question of space and its potential limits. The ancient idea of the music of the spheres, updated now with our modern understanding of gravitational waves, quantum fluctuations, and the harmonic patterns that seem to organize reality at every scale from the smallest to the largest. There's a sense in which the universe is constantly singing to itself, creating harmonies and rhythms through the motion of matter and energy across the vast expanses of space. These aren't melodies you could hear with your ears. Sound waves can't travel through the vacuum of space, but they're patterns of vibration and resonance that shape cosmic structure in ways that are surprisingly musical in their mathematical beauty. Gravitational waves, those ripples in space-time itself created by accelerating masses, represent the most literal version of cosmic music. When two black holes spiral into each other and merge, they create disturbances in the fabric of space that spread outward at the speed of light, carrying information about the violent dance that created them. These gravitational waves have frequencies and amplitudes that could, in principle, be converted into sound waves if we wanted to hear them. The LIGO detectors that first observed these cosmic songs actually did create audio recordings of black hole mergers, allowing us to literally hear the sound of space-time being disturbed by some of the most energetic events in the universe. But the music of space extends far beyond these dramatic gravitational crescendos. The cosmic microwave background itself carries acoustic signatures, frozen sound waves from the early universe that have been stretched by cosmic expansion into patterns we can observe today. These ancient acoustic patterns tell us about the resonant modes of the early universe, the ways that matter and energy preferred to organize themselves in the primordial cosmic medium. If you feel your mind resonating with these ideas of cosmic music, let it resonate peacefully. There's something deeply soothing about imagining the universe as a vast instrument, playing melodies too deep and slow for human ears to detect directly, but beautiful enough to inspire wonder in any consciousness capable of contemplating their mathematical structures. The mathematics of these cosmic harmonies reveals something profound about the organization of space on the larger scales. Just as musical instruments have natural resonant frequencies determined by their size and structure, the universe appears to have preferred scales of organization, characteristic distances and timescales that show up repeatedly in cosmic structure. Galaxies cluster together at certain preferred separations. The cosmic web of matter shows patterns that repeat at specific scales. Even the fluctuations in the cosmic microwave background display harmonic patterns that suggest the early universe was ringing like a cosmic bell, vibrating with modes determined by its size, composition, and fundamental properties. These harmonic patterns in cosmic structure might provide clues about whether space has natural boundaries or characteristic scales. If the universe is finite, even if unbounded, it would have natural resonant modes like a three-dimensional musical instrument. If it's infinite, the harmonic patterns might extend infinitely as well, creating endless variations on cosmic themes. The study of cosmic acoustics, the science of how sound waves and pressure fluctuations behaved in the early universe has revealed that space itself has acoustic properties. The speed of sound in the primordial cosmic medium, the way pressure waves propagated through space filled with matter and radiation, the resonant modes that could exist in cosmic geometries, all of these create a kind of cosmic acoustics that links the physics of sound to the structure of space-time. Recent observations have detected what astronomers call baryon acoustic oscillations, fossil sound waves from the early universe that have been imprinted on the current distribution of galaxies. These are like echoes of cosmic music that played billions of years ago, still detectable in the arrangement of matter across vast distances. These acoustic fossils suggest that the universe went through a phase when it was literally resonating, when pressure waves travelled through space creating patterns that would eventually influence where galaxies formed and how they clustered together. It's as if the universe sang itself into its current structure, using acoustic patterns as the template for cosmic architecture. The wavelengths of these ancient sound waves, stretched by billions of years of cosmic expansion, now span hundreds of millions of light years. What were once audio frequency vibrations in the dense early universe have become structural patterns visible in galaxy surveys that map billions of cosmic objects across vast volumes of space. This stretching of cosmic music by the expansion of space creates its own beauty. Imagine a song that has been playing for nearly 14 billion years, with each note gradually deepening in pitch as space grows larger, transforming from audible frequencies to radio waves to patterns in the distribution of galaxies themselves. If these ideas of cosmic music are lulling you towards sleep, embrace that gentle transition. The universe's music is patient enough to play for billions of years. It can certainly continue while you rest. Sometimes the deepest appreciation of cosmic harmonies comes not from conscious analysis, but from allowing your mind to drift in rhythm with the slow, vast melodies that organize reality itself. The harmonic organization of cosmic structure also suggests that space might have natural boundaries related to musical mathematics rather than geometric limits. Just as musical scales have natural intervals and harmonic relationships, space might have preferred organizational patterns that create domains of cosmic harmony, separated by boundaries where harmonic relationships change. These musical boundaries might be related to the fundamental frequencies of space-time itself, natural resonances that emerge from the quantum foam at the smaller scales and manifest as large-scale patterns in cosmic structure. The universe might be organized like a vast symphony, where different movements, different harmonic progressions create naturally separated sections while maintaining overall musical coherence. Recent theoretical work has suggested that even consciousness itself might be related to harmonic patterns in the organization of matter and energy. The neural oscillations that characterize brain activity, the way information is processed and integrated in conscious systems, the rhythms of attention and awareness, all of these display musical-like patterns that might connect individual consciousness to the broader harmonic organization of cosmic reality. Your capacity to appreciate the music of the spheres, to find beauty in mathematical harmonies and cosmic patterns, might represent space and time organizing themselves into resonance with their own deepest structures. Consciousness might be what happens when cosmic harmonies become aware of themselves, when the universe's music develops the capacity to listen to and appreciate its own melodies. Whether space ends in silence or continues its music infinitely, whether cosmic harmonies are finite compositions or endless variations on eternal themes, you're here now, participating in the universe's ongoing musical exploration of its own possibilities, adding your own notes of wonder and contemplation to the vast cosmic symphony. And as your awareness drifts toward the rhythm of sleep, perhaps you can hear in your own breathing, in your own heartbeat, in the gentle settling of your thoughts, echoes of the cosmic music that has been playing since the universe first learned to vibrate with possibility, first discovered that space itself could serve as the medium for harmonies, vast enough to contain galaxies, and gentle enough to lull consciousness toward peaceful rest. Section 21, The Psychology of Infinite Space. How our minds respond to boundlessness. There's something uniquely human about our need to understand boundaries, to know where things begin and end, to create mental maps that give us orientation in whatever space contains us. We evolved as creatures who navigated finite territories, who understood survival in terms of edges and barriers and the safe spaces contained between them. Our psychology is deeply shaped by millions of years of experience with limits. So when we encounter the possibility that space might be truly infinite, that it might extend forever without boundary or termination, something profound happens in the interaction between our finite minds and boundless cosmic reality. This encounter isn't just intellectual, it's psychological, emotional, perhaps even spiritual in its implications for how we understand our place in the vastness that contains us. As your consciousness rests in the gentle space between waking and sleeping, consider how infinity feels different from merely very large. There's a qualitative shift that occurs when we move from contemplating vast finite quantities to considering true endlessness. It's like the difference between imagining a road that's extremely long and imagining a road that literally never ends. The psychological impact is completely different. Infinity challenges the human tendency toward closure, toward resolution, toward the comfort of complete understanding. Our minds naturally seek patterns, boundaries, explanations that tie things together in coherent wholes. But infinity refuses this kind of cognitive closure, remaining forever open, forever unresolved, forever beyond the reach of complete comprehension. Yet there's also something deeply liberating about accepting infinity as a real possibility rather than fighting against its implications. When we stop trying to contain the cosmos within mental frameworks designed for finite territories, we open ourselves to a different kind of relationship with cosmic reality, one based on participation rather than ownership, on wonder rather than control. The medieval mystics understood something important about this psychological shift. They spoke of the soul's capacity to expand infinitely, to find rest not in finite boundaries, but in boundless possibility. They discovered that consciousness could find peace in infinity not by conquering it or comprehending it completely, but by recognizing its own participation in something larger than any individual mind could contain. Modern psychology has begun to study what researchers call infinity anxiety, the particular type of existential unease that some people experience when contemplating truly limitless possibilities. It's related to agoraphobia, the fear of open spaces, but it operates on conceptual rather than physical scales. Some minds find comfort in cosmic boundaries, in the idea that reality has limits that can be approached and understood. But others find that contemplating infinity produces the opposite effect, a sense of profound peace and connection, a feeling of being held by something so vast and generous that no individual concern could exhaust its capacity for containment. These people discover that their finite minds can rest comfortably within infinite space, like small boats finding calm waters in an endless ocean. If you're finding yourself in either category as we explore these ideas together, both responses are completely natural and valid. Infinity affects different minds in different ways, and there's no correct way to feel about the possibility of boundless space. What matters is finding your own comfortable relationship with cosmic mystery, your own way of participating in questions that might not have final answers. The psychological impact of infinite space also connects to questions about meaning and significance in human life. If space truly extends forever, containing infinite variety and infinite repetition, what makes any particular location, any individual existence, any specific moment of consciousness special or important? This question has puzzled philosophers for centuries, but perhaps it rests on a false premise, the assumption that significance requires rarity or uniqueness. A sunset doesn't become less beautiful because other sunsets exist elsewhere. A moment of love or wonder or peaceful contemplation doesn't lose its meaning because similar moments might occur in infinite variations across boundless space. Perhaps meaning emerges not from exclusivity but from depth, not from being the only example of something, but from being a perfect example of what's possible when matter and energy and consciousness organize themselves in particular ways. Your capacity for wonder, your ability to contemplate infinity while resting peacefully in your finite body, represents something remarkable regardless of how many other versions of consciousness might exist across infinite space. The psychology of infinite space also reveals something important about the human relationship to mystery itself. We're often told that science progresses by eliminating mystery, by replacing unknown quantities with known ones. But the study of cosmic infinity suggests that the deepest scientific insights often involve discovering more refined mysteries, more beautiful questions, more profound uncertainties that connect us to the fundamental nature of reality. Contemplating whether space ends doesn't diminish mystery, it deepens it, revealing layers of cosmic organization that are more subtle and strange than any simple answer could capture. The question transforms as we explore it, becoming not just a query about cosmic geography, but an inquiry into the nature of existence itself. If your thoughts are becoming as boundless as the space we're contemplating, let them drift without concern for reaching any particular destination. The exploration of infinity is not a problem to be solved, but a territory to be explored, not a puzzle to be completed, but a relationship to be developed over time through patient, gentle contemplation. Recent research in cognitive science has revealed that contemplating infinite spaces can actually enhance certain types of creative thinking, encouraging mental flexibility and openness to possibility that carries over into other areas of life. The mind that has learned to rest comfortably with cosmic uncertainty becomes more adaptable, more resilient, more capable of finding peace with the many smaller uncertainties of daily existence. There's also evidence that contemplating vast scales, whether spatial or temporal, can reduce anxiety and stress by putting everyday concerns into cosmic perspective. When you regularly remind yourself that you exist within a universe that might be infinite in its extent and eternal in its duration, the finite problems of daily life begin to feel more manageable, less overwhelming, more like temporary waves on an eternal ocean. This doesn't mean that everyday concerns become meaningless, quite the opposite. When you understand your life as a temporary organization of cosmic matter and energy, each moment becomes more precious, not less. When you recognize consciousness as an extraordinary achievement of cosmic evolution, each thought becomes more remarkable, not more trivial. The psychology of infinite space ultimately teaches us about the human capacity for awe, for wonder, for finding peace in mysteries that exceed our complete understanding. It reveals that our minds, evolved for navigating finite territories, can adapt to contemplating infinite possibilities without losing their basic orientation or emotional stability. As your consciousness settles into whatever relationship with cosmic infinity feels most comfortable and peaceful for you, remember that this adaptation itself is remarkable. You are finite matter and energy temporarily organized into a system capable of contemplating infinity, bounded awareness exploring boundless possibilities, a local intensification of cosmic matter, investigating the global properties of cosmic space. Whether space ends in boundaries we haven't discovered or continues infinitely with consistent properties throughout, your capacity to wonder about these possibilities represents something precious in the cosmic story. Matter and energy and space and time organizing themselves into consciousness, the universe developing the ability to contemplate its own nature through the gentle medium of minds like yours, resting peacefully in the infinite darkness while exploring the infinite questions that darkness contains. Section 22. The loneliness of vast distances. Isolation and connection in cosmic space. In the gentle quiet of this moment, as your breathing slows and your thoughts begin to soften towards sleep, let's contemplate together one of the most poignant aspects of cosmic space: the extraordinary loneliness of vast distances and the profound ways that space both separates and connects everything within its boundless embrace. The distances between objects in space are so enormous that they challenge our ability to feel emotionally connected to the cosmic community we're part of. Our nearest stellar neighbour, Proxima Centauri, is more than 4 light-years away, a distance so vast that if you could travel at the speed of our fastest spacecraft, the journey would take tens of thousands of years to complete. The nearest galaxy beyond our own Milky Way, the beautiful Andromeda spiral that you can sometimes glimpse as a faint smudge in dark skies, lies 2.5 million light-years distant. If our entire solar system were reduced to the size of a grain of sand, Andromeda would still be hundreds of miles away, a separation that makes interstellar distances seem intimate by comparison. These cosmic distances create a form of isolation that is both absolute and beautiful. Every star, every planet, every possible location where consciousness might have emerged to contemplate the cosmos exists in fundamental solitude, separated from its neighbours by gulfs of space so vast that meaningful communication across them approaches impossibility. Yet this isolation is not emptiness. The space between cosmic objects is filled with subtle connections, gravitational fields that link every particle of matter to every other particle across unlimited distances, quantum fields that extend throughout space, maintaining the possibility of particle creation and interaction, and the gentle warmth of the cosmic microwave background that bathes every cubic centimetre of space in the shared thermal memory of cosmic origins. If you feel a kind of cosmic loneliness settling over your thoughts as we contemplate these vast separations, let that feeling coexist peacefully with its opposite, the recognition that space doesn't separate us from, whether or not multiple universes actually exist beyond our own. Pondering them encourages a particular kind of intellectual humility and wonder. It reminds us that even our vast, mysterious, beautiful universe might be just one note in an infinite symphony of realities, just one story being told in an endless library of cosmic narratives. The implications stretch beyond cosmology into philosophy, into questions about meaning and uniqueness, and the significance of consciousness in a cosmos that might contain infinite variations on every theme. If every possible universe exists somewhere in the multiverse, what makes any particular universe special? What makes your experience, your consciousness, your moment of awareness unique? Perhaps the answer lies not in exclusivity, but in participation. You don't need to be the only conscious being in the only universe to be meaningful. Your awareness, your capacity for wonder, your ability to contemplate infinity while resting peacefully in your finite space, these remain profound regardless of how many other versions of reality might exist in dimensions we'll never access. As your mind drifts between the singular universe we can observe and the infinite possibilities we can only imagine, let yourself find peace in the mystery rather than anxiety about the unknown. Whether we live in one universe or countless trillions, whether consciousness is rare or abundant across the cosmic expanse, you are here now, thinking these thoughts, participating in the universe's ongoing attempt to understand itself. And that participation, that moment of cosmic self-awareness occurring in your brain as you contemplate these vast possibilities, is remarkable whether it's happening in one universe or infinitely many. You are the cosmos becoming conscious of itself, space and time organizing themselves temporarily into awareness, infinity contemplating its own nature through the gentle filter of a drowsy human mind settling towards sleep.